Imagine a realm where the very fabric of reality seems to stretch, twist, and distort, where the rules of physics bend in ways we can barely comprehend. In this extraordinary domain, stars emerge from chaos, and celestial bodies move in orbits that defy our conventional understanding. This is the universe we live in, an expanse filled with astonishing anomalies that continue to challenge the limits of human knowledge and beckon us to explore further. From the mysterious behavior of black holes to the elusive whispers of dark matter, the cosmos presents phenomena that seem almost beyond belief. Each new discovery forces us to rethink what we know about the universe, urging us to dive deeper into the uncharted realms of space and time. One of the greatest enigmas of the universe is dark matter. Though we now know it makes up nearly a quarter of the cosmos, its true nature remains one of the biggest unsolved riddles in modern science. Unlike ordinary matter, dark matter neither emits, absorbs, nor reflects light, making it virtually undetectable by conventional methods. We can only infer its existence by observing its gravitational influence on galaxies and the large-scale structure of the universe. Despite decades of research, the question of what dark matter truly is, what it's made of, and how it interacts with the rest of the cosmos remains as elusive as ever. Not far behind dark matter and mystery is dark energy, another force shrouded in uncertainty. This enigmatic energy seems to be responsible for the accelerated expansion of the universe. It accounts for a staggering 70% of the cosmos, yet scientists are still no closer to understanding what it is or where it comes from. Some hypotheses suggest that dark energy might be a fundamental property of space itself, while others propose that it could point to new physics beyond the scope of our current theories. The search to unlock the secrets of dark energy is one of the most significant frontiers in contemporary astrophysics. In the past few decades, scientists have also uncovered the phenomenon of fast radio bursts, short, intense bursts of radio waves that originate from deep space. These brief flashes last only a few milliseconds, yet they release an enormous amount of energy. The source of these bursts remains a mystery, with theories ranging from the collision of neutron stars to the possibility of extraterrestrial civilizations sending signals across the cosmos. Every new fast radio burst detected deepens the intrigue and raises profound questions about the nature of the universe. Another extraordinary mystery is the gamma ray burst, which represents the most powerful explosion known since the Big Bang. These bursts can unleash more energy in a few seconds than our sun will emit over its entire 10 billion year lifespan. While we understand that gamma ray bursts are linked to the collapse of massive stars or the merging of neutron stars, much about these events is still shrouded in mystery. What triggers these colossal explosions? How do they behave in space, and how do they interact with their surrounding environments? The answers to these questions continue to elude us, leaving these cosmic phenomena as some of the most profound and awe-inspiring mysteries of our time. At the heart of the universe's most intriguing puzzles are black holes, regions of space where gravity is so intense that nothing, no matter, no energy, not even light, can escape. These bizarre objects form from the collapse of massive stars, condensing all their mass into an infinitesimally small point, known as a singularity. In these regions, the very laws of physics as we understand them seem to break down. Black holes challenge not only our understanding of general relativity, but also our grasp of quantum mechanics. These singularities offer a window into the fundamental nature of reality, showing us just how little we truly know about the universe's deepest mysteries. When it comes to black holes, one of the most mind-bending aspects is the behavior of time itself. According to Einstein's theory of relativity, time is not a fixed, unchanging constant. It can stretch, bend, and compress depending on the gravitational field and the relative speed of an object. Near the event horizon of a black hole, the boundary beyond which nothing can escape, time appears to slow down drastically for an outside observer. For someone falling into the black hole, however, they would experience time normally, unaware of the distortion occurring around them. This strange phenomenon forces us to question our basic assumptions about the passage of time and the very nature of reality itself. These anomalies in the cosmos not only spark curiosity and wonder, but also serve as reminders of how much there is yet to discover. Each new insight we gain forces us to confront the limitations of our understanding, propelling us toward deeper inquiries and more profound questions. Whether it's the strange behavior of black holes, the mysterious forces of dark matter and dark energy, or the explosive power of gamma-ray bursts, the universe continues to surprise and confound us, urging us to push the boundaries of science and our comprehension of the cosmos. The more we explore, the more we realize how little we know, inviting us into a perpetual cycle of awe and inquiry. The nature of the singularity at the heart of black holes presents a monumental challenge to physicists. It is here that our current models of physics, including both general relativity and quantum mechanics, break down. At this mysterious point, our understanding falters, yet it is precisely here that the potential for discovery lies. If scientists can penetrate the enigma of what occurs within the singularity, it could unlock entirely new realms of scientific thought, bridging the gap between two foundational pillars of modern physics. This intersection of general relativity and quantum mechanics is regarded as one of the most profound, unresolved problems in the field. Decoding the secrets of black holes, thus, has the power to not only reshape the way we perceive black holes themselves, but also redefine the very nature of the universe. This pursuit demands a radical shift in how we think about space, time, and matter. In trying to comprehend the complex behavior of black holes, researchers are continually pushed to rethink the most basic principles of physics. The study of black holes forces us to question established truths and encourages a visionary approach to the vast mysteries of the cosmos. The existence of these enigmatic objects suggests that the universe is far more intricate and mind-boggling than we ever imagined, urging humanity to persist in its relentless quest for knowledge. Meanwhile, dark matter, an elusive substance that accounts for approximately 27% of the universe's mass, continues to confound scientists. Unlike ordinary matter, which constitutes the stars, planets, and all visible matter in the universe, dark matter neither emits, absorbs, nor reflects light. This makes it invisible to our current detection methods. Although we cannot observe dark matter directly, its presence is inferred by its gravitational effects on visible matter. One of the key pieces of evidence for dark matter comes from the way galaxies rotate and cluster. When astronomers first observed the motion of stars in galaxies, they found something unexpected. The stars on the outer edges of galaxies were moving much faster than expected, based solely on the visible mass. This discrepancy indicated the presence of an unseen force, dark matter, holding the galaxy together. Dark matter essentially acts as the unseen glue of the universe. Without it, galaxies would not be able to maintain their structure. In fact, the gravitational effects of dark matter are essential for understanding the rotation and the overall dynamics of galaxies. Beyond its role in galactic formation, dark matter offers profound insights into fundamental physics. Its existence forces scientists to look beyond the conventional theories of particle physics and entertain new possibilities. As researchers continue the search for direct evidence of dark matter, its true nature remains one of the greatest mysteries in modern science. Each new step in this search brings us closer to understanding the very fabric of reality, revealing that what we know is often just a small fragment of a much larger picture. Then there's dark energy, a mysterious force that constitutes roughly 70% of the universe's total energy content. Like dark matter, dark energy does not emit or interact with light, making it virtually invisible to our instruments, yet its influence on the universe is undeniable. The most compelling evidence for dark energy comes from the observation of distant galaxies. Not only are these galaxies receding from us, but they appear to be accelerating in their movement away from us, a phenomenon that contradicts the expectations based on the known laws of physics. This acceleration suggests the presence of an invisible force, pushing galaxies apart, in contrast to gravity, which would normally cause them to attract one another. This unknown force, now termed dark energy, is thought to be responsible for driving the expansion of the universe at an ever-increasing rate. As such, dark energy challenges everything we know about the cosmos. If the current trend of accelerating expansion continues, the universe could eventually reach a state known as the Big Freeze. In this future scenario, galaxies would drift too far apart to be observable, and the universe would become a cold, dark, and seemingly lifeless expanse. This raises profound questions about the ultimate fate of the cosmos and all the matter within it. Dark energy pushes the boundaries of our understanding, forcing us to reconsider foundational ideas about space, time, and gravity. As researchers continue to explore the implications of dark energy, it beckons us to ask more fundamental questions about the nature of the universe itself. Neutron stars, one of the most extraordinary objects in the universe, offer yet another window into the mysteries of the cosmos. These dense remnants are the aftermath of massive stars that have exploded as supernovae. What remains is an incredibly compact core, primarily composed of neutrons, which form when protons and electrons merge under the immense gravitational forces of the collapsing star. These neutron stars are often only around 20 kilometers in diameter, but their mass is greater than that of our Sun, resulting in an astonishingly high density. To put it in perspective, a single cubic centimeter of neutron star material would weigh as much as an entire mountain. One of the most fascinating features of neutron stars is their rapid rotation. Following the supernova explosion, the conservation of angular momentum causes these stars to spin at incredible speeds. In some cases, a neutron star can complete a full rotation in just a few milliseconds. This extreme rotation leads to the creation of beams of radiation emitted from the magnetic poles of the star. As the neutron star spins, these beams sweep across the sky. When the beams happen to point in our direction, we observe them as regular pulses of light, much like a cosmic lighthouse. These periodic pulses offer astronomers a unique opportunity to use neutron stars as cosmic clocks, allowing us to probe fundamental aspects of physics. Neutron stars are also known for their powerful magnetic fields, which can be over 1 trillion times stronger than the magnetic field of Earth. Some neutron stars, referred to as magnetars, exhibit especially intense magnetic fields, capable of producing bursts of X-rays and gamma rays. These bursts occur when the magnetic field undergoes rapid rearrangements, releasing vast amounts of energy. The energy emitted by these neutron stars far exceeds that of most ordinary stars, making them one of the most extreme and fascinating objects in the universe. Moreover, the study of neutron stars offers scientists a unique and extraordinary window into the behavior of matter under some of the most extreme conditions imaginable, where the very laws of physics are stretched to their breaking points. These compact, dense remnants of massive stars force us to rethink our understanding of nuclear forces, density, and the fundamental forces of nature. Within the depths of neutron stars, researchers uncover a miraculous environment, one that has become an invaluable research playground, constantly challenging our knowledge and expanding our scientific horizons. Every discovery surrounding neutron stars seems to unveil a new layer of mystery, fueling an insatiable curiosity to understand the intricate and sometimes baffling nature of the universe. Each breakthrough leads to more questions, revealing just how varied, diverse, and strange the cosmos truly is. Far beyond our familiar night skies, pulsars stand as some of the most captivating and enigmatic celestial objects. These highly magnetized, rapidly rotating neutron stars are the remnants of once massive stars that have exhausted their nuclear fuel and collapsed under their own gravity. What follows this collapse is a cataclysmic supernova explosion, leaving behind a core that is so dense it seems almost otherworldly. The density of neutron stars is difficult to fathom. A sugar cube-sized amount of material from a neutron star would weigh as much as an entire mountain on Earth. As these neutron stars spin at incredible speeds, they emit beams of electromagnetic radiation, which can be detected from Earth as regular pulses. These pulses act much like the beam from a lighthouse, sweeping across vast stretches of space, offering a glimpse into the workings of the universe from a distance. The significance of these pulses cannot be overstated in the context of cosmic research. Pulses are more than just signals. They serve as incredibly precise cosmic clocks, ticking away in space with remarkable stability. This consistency allows astronomers to measure time with an extraordinary degree of accuracy, opening doors to explore the most extreme conditions of matter, gravity, and nuclear physics. By studying these pulses, researchers gain invaluable insight into the behavior of matter under pressures and temperatures that cannot be replicated on Earth. Pulsars have also become crucial tools in probing some of the most groundbreaking phenomena of modern astrophysics. For instance, the detection of gravitational waves, ripples in the fabric of spacetime predicted by Einstein's theory of general relativity, was made possible through the observation of pulses. When two neutron stars orbit each other, they create these waves, which alter the timing of the pulses reaching Earth. By monitoring these subtle shifts, scientists have been able to confirm the existence of these elusive waves, thus validating a key prediction of Einstein's theory. In addition to their role in validating general relativity, pulsars have also been instrumental in studying the interstellar medium, the gas and dust that exists between stars. As pulsar signals pass through this medium, they interact with it, causing changes in the signal's characteristics. These variations allow researchers to map the composition and properties of the interstellar medium, providing a clearer picture of the space that exists between the stars. In this sense, pulsars act as cosmic laboratories, helping to uncover the hidden details of the universe that are otherwise invisible to us. Beyond their role as scientific tools, pulsars embody the mystery and wonder of the universe itself. Their study offers an endless journey into the unknown, with each new discovery further unraveling the fundamental laws of nature and the workings of the cosmos. Turning our attention to cosmic rays, we encounter another powerful phenomenon. These high-energy particles, which include protons, atomic nuclei, and heavier elements, travel through the vastness of space at nearly the speed of light. Their origins are often traced back to some of the most energetic and cataclysmic events in the universe, such as supernova explosions, black hole formations, and gamma-ray bursts. When these cosmic rays reach Earth, they interact with our atmosphere, producing a cascade of secondary particles that scientists can detect. These interactions provide researchers with a unique opportunity to study the origins and behavior of these high-energy particles and to decode the nature of the cosmic phenomena that produce them. Understanding cosmic rays is crucial to unlocking the mysteries of the most extreme events in the universe. For instance, the explosion of a supernova can accelerate particles to extraordinary speeds, propelling cosmic rays into space. By examining these rays, particularly their energy levels and composition, scientists can piece together the mechanisms of such explosive events, shedding light on how matter behaves under extreme conditions of pressure, temperature, and radiation. Furthermore, cosmic rays serve as messengers, carrying information from distant galaxies and regions far beyond our solar system. By analyzing the energy patterns and trajectories of these particles, astronomers can infer details about the environments from which they originated. In this way, cosmic rays allow scientists to map out the large-scale structure and dynamics of the universe, offering insights into regions of space that would otherwise be out of reach. The highest energy cosmic rays observed are thought to originate from some of the most powerful astrophysical sources, including supermassive black holes and the remnants of supernova explosions. These particles not only provide valuable clues about the energetic events that create them, but they also deepen our understanding of the very forces that shape the universe itself. By studying cosmic rays and their interactions, scientists unlock new avenues for understanding the origins, evolution, and behavior of the universe. They offer a glimpse into the hidden corners of space, revealing aspects of the cosmos that might otherwise remain obscured, and challenging our understanding of the forces and phenomena that govern the universe at its most extreme. Finally, astronomers have long been captivated by the elegance and mystery of spiral galaxies, those graceful, swirling collections of stars, gas, and dust that populate the universe. The study of these galaxies has yielded some of the most striking and unusual discoveries, such as the presence of trailing spiral arms that twist and curve in unexpected ways. Rather than following a simple, uniform structure, these arms often display intricate, feather-like patterns, suggesting that the dynamics of star formation and gravitational interactions play a crucial role in shaping the galaxy's overall structure. In some spiral galaxies, astronomers have observed the existence of central bars, long, thin structures that cut across the center of the galaxy, disrupting the traditional spiral arms. These bars are not just visual oddities. They have a profound impact on the dynamics of the galaxy. The bar structure influences the movement of gas and stars, causing them to orbit the bar while funneling gas toward the center. This influx of material can trigger bursts of star formation, leading to an increase in the brightness and activity at the galaxy's core. Many spiral galaxies also feature regions of intense star formation, often marked by the presence of luminous blue clusters. These clusters are the result of dense clouds of gas collapsing under their own gravity, initiating the rapid formation of new stars. This process can be violent, with massive stars forming at an astonishing rate and in turn undergoing supernova explosions. These explosions send shockwaves through the galaxy, which can trigger further rounds of star formation, contributing to the dynamic nature of the galaxy as a whole. The study of these fascinating galaxies not only offers a deeper understanding of how stars and galaxies evolve, but also provides insight into the larger-scale forces that shape the universe, revealing the intricate and ever-changing dance of matter across the cosmos. Astronomers have made fascinating observations in recent years, noting peculiarities that expand our understanding of the universe. One such discovery is the presence of ringed spirals, where concentric rings of stars and gas orbit the center of galaxies, creating an awe-inspiring visual spectacle. These rings are not mere curiosities. They provide vital clues to the complex histories of galaxies. Such features likely result from interactions with nearby galaxies, which can cause significant gravitational disturbances. Studying these ringed structures doesn't just enhance our knowledge of spiral galaxies, it also unveils the intricate, dynamic nature of the cosmos, showing us that even the smallest galaxies are shaped by complex forces beyond their immediate bounds. Another extraordinary phenomenon is gravitational lensing, a captivating effect first predicted by Albert Einstein's theory of general relativity. This occurs when a massive object, like a galaxy or a galaxy cluster, lies between an observer and a distant source of light. The gravity of these massive objects bends the light from the more distant galaxies, much like a convex lens bends light. This bending doesn't just distort the appearance of galaxies, it can also magnify them, sometimes creating multiple images of the same distant galaxy. Gravitational lensing serves as a cosmic magnifying glass, allowing astronomers to peer into galaxies that would otherwise be too faint or distant to detect. By studying these distorted and magnified images, scientists can uncover valuable details about the distant galaxies, such as their size, shape, and the distance from Earth. More than just a tool for observation, gravitational lensing also provides insight into the enigmatic dark matter, an invisible substance that exerts a gravitational influence on galaxies, but eludes direct detection. As light from distant galaxies is bent by dark matter's gravitational pull, astronomers can infer its distribution across the cosmos. This method also reveals crucial information about the expansion of the universe. As light travels through various gravitational fields, its bending traces the expansion rate of the universe, helping scientists chart the course of cosmic evolution over billions of years. Gravitational lensing is not just an optical curiosity. It's an indispensable tool in modern astronomy, offering us a glimpse into the universe's distant past. It sheds light on the formation and evolution of galaxies, some of which formed when the universe was still in its infancy, offering profound insights into the fundamental forces that shape the cosmos. Then there is the cosmic microwave background radiation, often referred to as the CMB. This faint afterglow of the hot plasma that filled the universe just 300,000 years after the Big Bang is one of the strongest pieces of evidence supporting the Big Bang theory. While the CMB appears remarkably uniform across the sky, astronomers have identified intriguing anomalies within it that challenge our current understanding of the universe. One such anomaly is the cold spot, an area of the CMB that is significantly cooler than its surrounding regions. This cold region has sparked intense debates among scientists. Some speculate that it could be a sign of an enormous supervoid, an enormous region of empty space stretching over 1 billion light-years. Others propose that it might be a sign of unfamiliar structures or phenomena that remain poorly understood, possibly hinting at new physics or alternate models of cosmic evolution. These anomalies challenge the very framework of cosmology, urging scientists to probe deeper into the mysteries of the universe. Additionally, there are peculiar alignments of temperature fluctuations in the CMB that seem to correlate with the large-scale structure of the universe. Some areas of the CMB appear to be aligned in ways that suggest these patterns are not random. This has raised questions about the very fabric of the universe. What causes these alignments? Could they be related to the effects of gravitational waves from the early universe or to phenomena during the period of cosmic inflation? These anomalies invite us to venture beyond our traditional models, urging us to explore concepts such as dark matter, dark energy, and the true nature of spacetime itself. As we continue to study these features, we may uncover deeper insights into the universe's origins and its ultimate fate. The search for answers to these cosmic puzzles has just begun, promising an exciting future for the field of cosmology. Then, there is the concept of the multiverse, an idea that suggests the existence of multiple, possibly infinite universes beyond our own. This concept has captured the imagination of both scientists and the general public alike. Several compelling theories have emerged to explain this fascinating idea, each rooted in different aspects of physics and cosmology. One of the most well-known theories comes from quantum mechanics. According to this interpretation, every time a decision is made or an event occurs with multiple possible outcomes, a new universe is created for each of these outcomes. Known as the many worlds interpretation, this theory suggests that all possible versions of reality, those we live in and those that never come to pass, exist simultaneously. This theory proposes a vast, branching tree of universes, each one reflecting a different choice or possibility. A second theory stems from cosmic inflation, the rapid expansion of the universe that occurred just after the Big Bang. This theory posits that different regions of space may have stopped inflating at different times, leading to the formation of distinct bubbles, or universes, each with its own unique properties. These universes could each have different physical laws, constants, and dimensions. This concept, known as the inflationary multiverse, extends the boundaries of our understanding beyond the universe we observe, suggesting that our cosmos is merely one bubble in an infinite sea of universes, each with its own reality. Another intriguing perspective comes from string theory, which seeks to unify the fundamental forces of nature. String theory suggests that there are many possible configurations of the universe, each leading to different sets of physical laws and constants. In this view, the universe we inhabit could be just one among many, with each configuration representing a unique set of physical rules. String theory's multiversal landscape hints that the laws governing our universe are just one possibility in a vast speculative framework, one that continues to evolve as new discoveries are made. As scientists delve deeper into the mysteries of string theory and other cosmological models, they uncover new insights that may one day confirm the existence of the multiverse. Whether we will ever be able to prove this mind-bending idea remains uncertain, but the prospect of infinite realities challenges everything we know about the universe and our place within it. The study of these extraordinary phenomena, gravitational lensing, the CMB, and the multiverse, promises to reshape our understanding of the cosmos. Each new discovery uncovers a layer of the universe previously hidden, pushing the boundaries of science and inviting us to explore the farthest reaches of reality itself. Our journey through the cosmos has only just begun. The anthropic principle introduces a deeply philosophical dimension to the conversation about the universe. It asserts that the particular conditions we observe in our universe are not arbitrary, but must allow for the existence of conscious observers like us. According to this principle, among the countless universes that may exist, each governed by its own set of physical laws, ours is one that is finely tuned to support life. This concept, often referred to as the fine-tuning of the universe, raises the idea that our universe is not only special, but seemingly designed to accommodate the existence of beings capable of contemplating it. As we delve into these theories, we are invited to engage with profound questions about the very nature of reality. What does it mean to exist in a universe that allows for conscious life? And if there are indeed other universes, how do we find ourselves in the one that sustains us? The multiverse theory, which posits the existence of multiple universes, further challenges our understanding of existence itself. It suggests that the cosmos might be far larger and more intricate than we ever imagined, with each universe possibly operating under its own unique set of physical laws. This idea of infinite variations in reality pushes the boundaries of our intellectual and philosophical explorations, leaving us in awe of the cosmic complexity. Amid these bold theoretical frameworks, string theory emerges as a captivating attempt to unify the forces of nature. At its heart, string theory challenges the traditional view of the universe's building blocks. Rather than being composed of point-like particles, as we once thought, the universe's fundamental components are instead tiny, vibrating strings. The way these strings vibrate determines the properties of the particles we encounter, such as their mass and electric charge. This shift in perspective, moving from particles to strings, offers a revolutionary way of thinking about the structure of the cosmos. String theory suggests that the four fundamental forces we observe, gravity, electromagnetism, and the nuclear forces, might be mere manifestations of a deeper, unified reality. But this theory goes even further, proposing the existence of additional dimensions beyond the familiar three of space and one of time. Some versions of string theory predict as many as 10 or 11 dimensions, hidden from our direct perception but intricately woven into the very fabric of the universe. These dimensions, though imperceptible, are thought to play a crucial role in shaping the physical laws that govern the cosmos. One of the most tantalizing aspects of string theory is its potential to bridge the gap between two of modern physics' most successful yet incompatible pillars, gravity and quantum mechanics. Quantum mechanics excels at explaining the behavior of matter at the smallest scales, while general relativity describes the dynamics of large-scale objects like planets and galaxies. For decades, these two theories have resisted reconciliation. String theory promises to unify them, offering the potential for a deeper understanding of phenomena such as black holes, the Big Bang, and the fundamental structure of space-time itself. Despite its elegance and the promise it holds, string theory remains largely speculative, with many of its predictions still untested by experiment. Nevertheless, it has sparked an explosion of research, influencing various fields of physics and mathematics. As scientists continue to probe its implications, string theory could fundamentally alter our perception of the universe. Instead of seeing the cosmos as a collection of particles and forces, we might begin to envision it as a vast, intricate tapestry of strings vibrating in multiple dimensions, the full extent of which we are only beginning to comprehend. Alongside string theory, the concept of wormholes has captured the imagination of both scientists and science fiction enthusiasts alike. Wormholes, often described as tunnels through space-time, represent a fascinating possibility for faster-than-light travel. Imagine being able to bypass the vast emptiness of space and instead traverse an instantaneous shortcut between two distant points in the universe. If such structures exist, they could fundamentally alter our understanding of space and time, challenging our conventional notions of distance and travel. But wormholes are not just theoretical tools for interstellar travel. They also prompt a rethinking of time itself. Some hypotheses suggest that wormholes could offer a means of traveling not just across space, but also through time. Could someone, for instance, journey back to witness historical events or even change the course of history? Such questions raise profound philosophical issues about causality and the linearity of time. Moreover, wormholes may offer a new way of understanding the enigmatic behavior of black holes. Black holes, regions where gravity is so intense that not even light can escape, are one of the greatest mysteries in modern physics. Some theories propose that black holes could be connected to wormholes, potentially serving as entrances to other parts of the universe. This tantalizing possibility suggests that deep within the cosmos there might be hidden connections between regions of space that are currently unreachable, offering the potential for interaction between distant realms of existence. However, despite their allure, wormholes remain speculative. Current physics does not provide a practical method for creating or stabilizing these hypothetical structures. To form a wormhole, scientists believe we would need exotic matter with negative energy density, a substance that has not been observed. Still, The very idea of wormholes challenges the boundaries of what we consider possible and invites us to dream of a universe far more complex and interconnected than we ever imagined. Another hypothesis that stretches our understanding of the universe is the concept of a cyclic universe. According to this model, the cosmos does not have a singular beginning and end as traditionally thought, but instead undergoes an endless series of cycles. Each cycle begins with a Big Bang, expands to a maximum size, and then contracts back to a dense hot state before beginning anew with another Big Bang. This cyclical view of the universe stands in stark contrast to the linear timeline of a universe that began in a single event and will eventually reach a definitive conclusion. The idea of a cyclic universe forces us to reconsider our understanding of time and existence. If the universe undergoes an eternal cycle of birth, death, and rebirth, what does it mean for the concepts of beginning and end? In this model, time itself becomes more fluid, less like a straight line and more like a repeating loop. Each cycle could reset the stage for new physical laws or conditions, offering endless possibilities for the evolution of the cosmos. The cyclical universe hypothesis raises profound questions about the nature of time and whether it is truly linear or part of a much more intricate and repeating pattern that stretches beyond our comprehension. Ultimately, these theories, whether concerning the fine-tuning of the universe, string theory, wormholes, or the cyclic nature of the cosmos, invite us to broaden our understanding of reality. They challenge our assumptions and spark our imagination, encouraging us to look beyond the limits of current scientific knowledge and explore the vast, uncharted frontiers of the universe. As we continue to investigate these mysteries, we are forced to confront the fundamental questions. What is the true nature of existence? And what role do we play in this extraordinary, unfathomably complex universe? The concept cyclic universe is not just a mere theoretical abstraction. It compels us to rethink fundamental questions about life, consciousness, and the nature of existence itself. If the universe indeed has existed in various forms throughout infinite cycles, this raises profound questions about the permanence, or perhaps the impermanence, of actions and events. In such a universe, the conditions of one cycle could potentially influence the next, blurring the lines between past, present, and future realities. This idea opens up a realm of possibilities where the events of previous universes might leave echoes that resonate in the universe we inhabit today. Such a vision of reality invites us to reconsider our place in the cosmos. Are we merely a fleeting moment in a much larger eternal story? The notion that we might only be one chapter in an endless, ever-revolving narrative challenges our perception of time and space. It forces us to confront the idea that our lives may be part of a cosmic cycle far larger than we can fully comprehend. This shift in perspective isn't just an intellectual exercise. It invites deep philosophical reflection about our purpose in a universe that may stretch infinitely both backward and forward in time. While the cyclic universe theory remains an area of active research and debate within the scientific community, its very possibility encourages us to question our assumptions about the nature of existence. The idea of an ever-changing cosmos as opposed to a static, unchanging one challenges the traditional models of physics and invites us to embrace a more dynamic understanding of the universe. It suggests that the universe is not a closed, finished entity, but rather a constantly evolving system, where each cycle may bring new opportunities, challenges, and revelations. This notion leaves us with a sense of wonder, encouraging us to rethink our relationship to the cosmos and our place within it. Similarly, the exploration of quantum gravity represents a cutting-edge frontier in physics, one that promises to radically reshape our understanding of the universe. Quantum gravity attempts to bridge the gap between two pillars of modern physics, general relativity and quantum mechanics. While general relativity describes the behavior of massive objects and the fabric of space-time on large scales, quantum mechanics governs the behavior of particles at the smallest scales. The reconciliation of these two theories could offer profound insights into the mysteries of black holes, those enigmatic cosmic objects that have long fascinated scientists and laypeople alike. Traditionally, black holes have been understood through the lens of general relativity. According to this framework, black holes form when massive stars collapse under their own gravity, creating a singularity where space-time curves infinitely. Once something crosses the event horizon, the so-called point of no return, it is thought to be lost to the universe forever. This notion of irrevocable loss has been a central feature of black hole theory for decades. However, the advent of quantum mechanics has introduced new complexities, particularly in relation to the conservation of information. Quantum gravity seeks to unify these two realms, and in doing so raises an intriguing proposition: the idea that information, the very essence of all physical states, cannot be destroyed. This idea challenges the traditional view that once something falls into a black hole, it is gone for good. According to quantum principles, there must be some mechanism by which this information is preserved, even if it is no longer accessible in its original form. This paradox has come to be known as the black hole information paradox, a problem that continues to baffle scientists. Some theorists have proposed that rather than being obliterated, the information might be stored on the event horizon itself, encoded in a two-dimensional form, a concept known as holography. This theory suggests that the three-dimensional information about objects that fall into a black hole might be written on its two-dimensional surface, similar to how information is encoded on the surface of a hologram. This radical idea challenges our understanding of space, time, and gravity itself. Even more remarkably, recent research has suggested that black holes might not be entirely black after all. They could potentially emit particles through a process known as Hawking radiation, named after physicist Stephen Hawking. This phenomenon implies that black holes might not be completely isolated from the rest of the universe, as previously thought. Instead, they may allow information to escape, albeit in a transformed or altered state. The implications of this theory are profound, as they suggest that the fate of objects falling into black holes might not be as final as we once believed. As scientists continue to explore the intersection of quantum mechanics and general relativity, our understanding of black holes and the fundamental laws of physics will undoubtedly evolve. New theories and discoveries may emerge that challenge and refine our existing models of the cosmos, leading to an ever deeper comprehension of the universe's most elusive mysteries. Another area of scientific inquiry that plays a significant role in cosmology is chaos theory, a branch of mathematics and physics that deals with complex systems that are highly sensitive to initial conditions. This theory suggests that small variations in the starting conditions of a system can lead to vastly different outcomes, making long-term predictions inherently uncertain. The principle of chaos is often illustrated by the so-called butterfly effect, which suggests that the flap of a butterfly's wings in one part of the world could theoretically set off a tornado in another. While this may sound like an exaggeration, the underlying idea is that small, seemingly insignificant events can have profound and unpredictable consequences over time. In the realm of cosmology, chaos theory has important implications, particularly when it comes to understanding the behavior of planetary systems and the dynamics of galaxies. Planetary orbits, for example, are not always stable. They can be influenced by gravitational interactions with other celestial bodies, leading to changes in their trajectories over time. Even tiny shifts in the position or velocity of one planet can have cascading effects on the entire system, causing significant shifts in the orbits of other planets. This sensitivity to initial conditions makes it extremely difficult to predict the long-term behavior of planetary systems with any degree of accuracy. Over the course of millions or even billions of years, tiny variations in the orbits of planets can lead to dramatic shifts in the configuration of the entire system. For instance, a seemingly minor change in the orbit of one planet could eventually lead to the destabilization of the orbits of other planets, possibly resulting in catastrophic collisions or the ejection of planets from the system altogether. Chaos theory underscores the complexity and unpredictability of the universe. It reminds us that even in a seemingly orderly and deterministic system, small fluctuations can lead to unexpected and sometimes profound outcomes. As we continue to explore the cosmos, chaos theory will undoubtedly play an important role in helping us understand the long-term behavior of celestial bodies and the intricate web of interactions that shape the universe. Moreover, chaos theory plays a pivotal role in shaping our understanding of stellar evolution. As stars progress through their life cycles, their behavior and internal processes evolve, often in unpredictable ways. These shifts, driven by seemingly small and insignificant changes, can push a star onto entirely different evolutionary paths. This concept is especially crucial when investigating extraordinary cosmic phenomena such as supernova explosions, the formation of neutron stars, and the birth of black holes. In these contexts, the chaotic behaviors that emerge challenge our ability to accurately predict the precise timing or nature of these events. This unpredictability adds an element of uncertainty to many cosmic predictions, forcing us to acknowledge that some aspects of the universe are inherently beyond our control or comprehension. While chaos theory underscores the randomness that underlies these cosmic events, it also reveals the stunning complexity and intricate beauty of the universe itself. The delicate balance between order and chaos invites scientists to probe deeper into the fundamental laws that govern celestial mechanics. This ongoing pursuit pushes the limits of our understanding, inviting constant refinement of the models and theories that explain the cosmos. As cosmologists journey into the heart of these complexities, they uncover a universe that is rich with surprises, where every new discovery expands the boundaries of human knowledge and inspires awe at the vastness and wonder of the cosmos. Simulations of alternate universes serve as invaluable tools in this quest for understanding. These theoretical models allow researchers to experiment with different conditions, varying the laws of physics and adjusting initial parameters to see how they might influence cosmic outcomes. By examining these alternate realities, scientists gain a broader perspective on the universe we inhabit. They can compare and contrast these hypothetical scenarios with our actual universe, revealing how subtle changes could result in radically different cosmic structures or entirely different paths of evolution. One of the most captivating aspects of these simulations is their ability to illustrate the delicate balance of forces that sustain our universe. For example, if the strength of gravity were altered, the formation of stars, galaxies, planets, and even life as we know it could be entirely prevented. By manipulating these parameters, scientists can observe firsthand how small variations can lead to vastly different outcomes. Some simulations might even suggest that entire structures, such as galaxies, could be impossible under different conditions, offering profound insights into why our universe is fine-tuned to support life in the specific way that it does. These simulations also provide a testing ground for cosmological theories. By modeling the evolution of the universe from the Big Bang onwards, scientists can explore how galaxies cluster, how dark matter behaves, and how cosmic expansion unfolds under a variety of conditions. This process allows them to assess the accuracy of our current theories, refining our understanding based on the results of these virtual experiments. This iterative process of modeling, comparison, and refinement is fundamental to advancing our knowledge of the universe and its complex workings. Ultimately, simulations of alternate universes do more than just capture our imagination. They serve as critical experiments that deepen our understanding of the cosmos. These virtual realities challenge our assumptions, pushing the boundaries of what we know and fueling new avenues of inquiry. As scientists continue to explore these alternate possibilities, they gain insights that may shed light on why our universe is uniquely suited for life, thereby enriching our quest for knowledge and our appreciation of the universe's vast and mysterious nature. The holographic principle offers another profound shift in our perception of the universe. At its heart, this principle suggests that all the information contained within a three-dimensional space can be represented as a two-dimensional surface. This idea originated in the study of black hole physics, initially proposed by scientists like Gerard Hooft and Leonard Susskind. They observed that the amount of information that can be contained within a black hole is proportional to its surface area, not its volume. This insight laid the groundwork for the holographic principle, which has since become a cornerstone of modern astrophysical thought. What makes the holographic principle so compelling is its implications for the very nature of reality. It challenges the traditional understanding of dimensions by suggesting that our familiar three-dimensional world might actually be a projection of information encoded on a distant two-dimensional surface. This perspective invites scientists to reconsider how we think about space, time, and the fundamental structure of the universe. It also prompts deeper investigations into the relationships between gravity, quantum mechanics, and the nature of space-time itself. In practical terms, the holographic principle offers potential pathways to resolve some of the most elusive puzzles in physics. It could provide new insights into the behavior of black holes and even the very fabric of the universe. This principle has also reinvigorated interest in string theory, where ideas about extra dimensions and supersymmetry dovetail with the holographic outlook. As researchers continue to explore this concept, they are uncovering new ways to bridge the gaps between general relativity, which governs large-scale cosmic structures, and quantum mechanics, which rules the subatomic world. The holographic principle, in this sense, represents a convergence of ideas that could ultimately reshape our understanding of the universe. Parallel dimensions are another concept that stretches our comprehension of reality itself. Imagine a reality where every decision you make leads to the creation of a new dimension, an entirely different world that runs alongside our own. This idea of parallel dimensions challenges the traditional notion of a singular linear reality and suggests that the cosmos is a vast, interconnected web of possibilities. Each choice we make could, in theory, create a new branch in the tree of existence, generating pathways we may never experience, but which could theoretically coexist alongside our own life. At the heart of this idea lies the multiverse theory, which proposes that our universe is just one of an infinite number of universes. Each of these universes might operate according to its own unique set of physical laws or timelines, giving rise to entirely different versions of ourselves and alternate realities. In one such dimension, you might be a scientist delving into the mysteries of black holes, while in another, you might have chosen an entirely different path in life. This notion expands our understanding of existence itself, inviting us to reconsider what reality truly is and how we fit into the vast, ever-expanding cosmos. The multiverse theory challenges the boundaries of our imagination, offering a vision of existence that transcends the limitations of a singular linear path. Understanding the existence of parallel dimensions could have profound implications in fields like physics and cosmology, urging us to challenge the very fabric of how we view time and space. Instead of perceiving moments as isolated, sequential events, the concept proposes that all events exist simultaneously, woven together in an intricate, interconnected tapestry. This radical idea could offer new insights into phenomena that have long puzzled scientists, particularly in the realm of quantum physics. Quantum particles, for example, often behave unpredictably, appearing to exist in multiple states at once, a behavior that might be explained by the presence of parallel dimensions. This notion forces us to reconsider our traditional perceptions of reality, suggesting that the universe is not as fixed as we once believed. The possibilities seem endless. Could parallel dimensions offer explanations for unexplained quantum phenomena, or even be the key to understanding the strange forces of the universe? As we delve deeper into these concepts, we may begin to unlock groundbreaking advancements, not just in science, but in technology as well. Our understanding of the cosmos, and perhaps even our very place within it, may shift dramatically. The exploration of parallel dimensions isn't just a matter of theoretical physics. It's a doorway to rethinking fate, free will, and the nature of existence itself. Are our lives truly determined by a single unchangeable timeline, or are there alternate versions of us living in parallel realities, making different choices? As our technology advances, we're poised to explore these questions with more clarity. The idea that there could be layers upon layers of realities hidden just out of our reach tantalizes our imaginations and fuels our desire to explore further. Recent advancements in technology have ushered in a new age for astrophysics, arming scientists with the tools to uncover deeper secrets about the universe. One such breakthrough is the development of ultra-sensitive telescopes, designed to observe celestial phenomena with unprecedented detail. These state-of-the-art instruments, both ground-based and space-based, enable astronomers to detect faint light from the farthest reaches of space, with capabilities like observing gravitational lensing or capturing images of distant galaxies. These telescopes challenge current theories and open doors to new, exciting possibilities. In addition to telescopic advancements, computational modeling and simulations have reached new heights. As computing power continues to grow, so does our ability to model the most intricate cosmic events, be it the formation of galaxies, the behavior of black holes, or the mysteries surrounding dark matter. Today's high-performance computers can process vast amounts of data, allowing scientists to conduct complex calculations far more efficiently than ever before. This not only aids in visualizing theories, but also allows researchers to predict phenomena that have yet to be observed, thus sparking new hypotheses that could change the way we view the universe. Artificial intelligence, AI, is also transforming the landscape of astrophysics. Machine learning algorithms now help sift through massive data sets, uncovering patterns that may otherwise be invisible to human eyes. One area where AI has proven invaluable is in the search for exoplanets. By analyzing light curves from distant stars, AI systems can detect subtle changes that suggest the presence of orbiting planets. This, in turn, could bring us closer to discovering extraterrestrial life, a discovery that would fundamentally alter our understanding of the cosmos. Simultaneously, the field of particle physics continues to address fundamental questions about the universe's composition. With the help of particle accelerators and detectors, scientists are pushing the boundaries of what we know, probing the elusive components of dark matter and dark energy. These mysterious substances, believed to influence the expansion and structure of the universe, remain largely unknown. As we develop new technologies to study them, our understanding of the universe deepens, offering fresh perspectives on age-old mysteries that continue to captivate our collective curiosity. Among the vast expanse of the universe, astronomers have discovered a mind-boggling array of exoplanets that challenge our definitions of what a planet can be. Some of these worlds are remarkable for their bizarre and extreme characteristics. Take, for example, the planet WASP-121b, a gas giant orbiting a star about 10 times closer than Earth's distance from the Sun. This hot Jupiter's proximity to its star causes temperatures to soar above 1,600 degrees Celsius, hot enough to melt metals. Its atmosphere, a mix of elements like magnesium and iron, creates an otherworldly sight, molten metal raining down from the sky. Such extremes push the limits of what we thought was possible for planetary environments. Then there's LHS 3844b, a planet located about 45 light-years away, notable for its lack of an atmosphere. Without an insulating layer of gases, LHS 3844b experiences extreme temperature fluctuations, with day-side temperatures reaching scorching highs, while its night side plunges into a frigid cold. This stark contrast raises intriguing questions about the planet's surface. Could it be composed of dark basaltic rocks, possibly shaped by volcanic activity? The planet's inhospitable conditions offer a rare opportunity to study how planets might evolve under extreme circumstances. Perhaps even more remarkable is HD 199733b, a planet where storms rage at unimaginable speeds. Winds here exceed 2,000 kilometers per hour, fast enough to turn raindrops into glass-like projectiles. The planet's intense blue color, likely caused by silicate particles suspended in its atmosphere, gives it an eerie, almost alien appearance. Yet the beauty of this planet is matched only by its terrifying, tumultuous weather systems, making it both a captivating and dangerous world. These celestial discoveries force us to rethink what is possible in the universe. The diversity of exoplanets reveals that planets come in an astonishing variety of forms, some of which challenge even the most fundamental assumptions about planetary formation and habitability. As we continue to push the boundaries of exploration and technology, we are faced with the realization that the cosmos is far more complex and more mysterious than we ever imagined. The deeper we look, the more we uncover, and with each discovery, the universe becomes an even more fascinating place. Lastly, we cannot overlook K2-141b, an exoplanet that has earned its nickname as the lava planet. This distant world is truly a place like no other, with oceans of molten rock instead of water. The extreme temperatures, combined with its close proximity to its star, create an environment where liquid rock flows in rivers, continuously reshaping the landscape. In contrast to Earth, where water forms rivers, lakes, and oceans, K2-141b boasts these fiery, ever-changing rivers of lava. These extraordinary characteristics stretch the boundaries of what we consider possible for a planet, expanding our understanding of the diverse conditions that may exist beyond our solar system. They fuel our curiosity about whether life could survive in such extreme, hostile environments. Identifying potentially habitable planets in distant solar systems is no small feat. It requires a combination of advanced technology, a deep understanding of what makes a planet capable of supporting life, and an open mind to possibilities beyond our current knowledge. The search for such planets begins with a focus on what scientists call the habitable zone, the region around a star where conditions might be just right for liquid water to exist. This zone is crucial because water, as we know, is one of the essential ingredients for life. The size of the star, its temperature, and the distance between the star and the planet all play critical roles in determining whether a planet falls within this habitable zone. To explore these distant worlds, scientists rely on some of the most powerful telescopes ever built. The Kepler Space Telescope, for instance, has been instrumental in this search. By monitoring thousands of stars, it detects tiny dips in their brightness, which occur when a planet passes in front of its host star. This method, called the transit method, allows researchers to infer key details about the planet, including its size and orbital period. This data is vital for determining whether the planet could potentially exist in the habitable zone of its star. Once a potential exoplanet is identified, scientists turn to a technique called spectroscopy to analyze its atmosphere. By studying the light that either passes through or reflects off the planet's atmosphere, researchers can detect the presence of various chemical elements and compounds. The fingerprints left by these elements in the light can tell scientists whether oxygen, carbon dioxide, methane, or other crucial molecules exist, potential indicators of biological processes. In addition to the atmosphere, the planet's stability is another factor that must be considered. A planet with a stable climate, a balanced temperature, and a protective magnetic field stands a better chance of maintaining conditions suitable for life. Through these combined methods, astronomers are continuing to expand our knowledge of the distant worlds that could potentially harbor life, always driven by the exciting possibility of discovering something truly extraordinary in the vastness of space. Pluto, once celebrated as the 9th planet in our solar system, has undergone a remarkable transformation in how we view it. Since its discovery in 1930, it was initially classified as a planet, but in 2006, the International Astronomical Union redefined it as a dwarf planet, sparking considerable debate. Despite this reclassification, Pluto has remained a subject of intrigue, especially after the revelations brought forth by the New Horizons mission. In 2015, this spacecraft passed by Pluto, sending back breathtaking images and data that unveiled the dwarf planet's stunning geological features. From vast icy plains to towering mountains, Pluto's surface is far from static. Moreover, scientists now believe that Pluto may harbor subsurface oceans, raising questions about the potential for hidden water beneath its frozen exterior. In addition to its dynamic surface, Pluto's atmosphere is another surprising aspect of this distant world. Though it is thin, it consists mainly of nitrogen, with traces of methane and carbon monoxide. Scientists have observed seasonal changes in the atmosphere, which expands and contracts as Pluto moves closer to and farther from the Sun along its elliptical orbit. These seasonal variations suggest that Pluto is more similar to Earth in terms of atmospheric dynamics than many initially believed. However, despite these fascinating discoveries, the debate over Pluto's planetary status remains unresolved. Some astronomers argue that Pluto's unique characteristics, its complex atmosphere, diverse geology, and potential subsurface water, warrant a redefinition of what constitutes a planet. As scientific knowledge continues to evolve, so too may our understanding of Pluto and the broader definition of planets. Pluto's story serves as a powerful reminder of how science is always in flux, continually refining our perceptions as we uncover more about the cosmos. Meanwhile, Venus, the second planet from the Sun, presents yet another captivating enigma. Despite its extreme heat, surface temperatures that can soar to around 900 degrees Fahrenheit, Venus's thick atmosphere is composed predominantly of carbon dioxide with clouds of sulfuric acid. This dense atmosphere creates an intense greenhouse effect, trapping heat and making Venus even hotter than Mercury, despite being farther from the Sun. The atmosphere's composition and its effects on the planet's surface have long puzzled scientists, raising critical questions about the planet's potential for sustaining life. One of the most fascinating features of Venus's atmosphere is its superrotation. While Venus itself rotates on its axis very slowly, taking about 243 Earth days to complete a single rotation, the atmosphere behaves in a radically different manner. At high altitudes, the clouds whip around the planet in just about 4 Earth days, creating wind speeds that can exceed 150 miles per hour. This dramatic difference between the planet's slow rotation and its rapidly moving atmosphere has intrigued scientists, prompting them to investigate the complex interactions that drive such extraordinary atmospheric dynamics. The causes of these fast-moving winds may be linked to temperature, pressure, and the unique atmospheric composition, offering further insights into how planetary atmospheres work under extreme conditions. Venus continues to be a planet of great interest, as scientists seek to understand its strange and violent environment, pushing the limits of what we know about planetary climates and their ability to support life. Scientists have been unraveling a series of perplexing and mysterious phenomena that continue to challenge our understanding of the cosmos. One such enigma is the detection of phosphine gas in trace amounts on Earth. Phosphine, a compound linked to biological processes, is primarily associated with microorganisms. On Earth, it is produced by certain microbes thriving in oxygen-deprived environments. However, when phosphine was detected in the dense, hostile atmosphere of Venus, it sparked a debate that goes beyond the mere presence of a gas. While the discovery of phosphine on Venus does not directly indicate the presence of extraterrestrial life, it presents a tantalizing puzzle. The harsh conditions on Venus, highly acidic clouds, temperatures exceeding 450 degrees Celsius, and crushing atmospheric pressure, make it difficult for life as we know it to thrive. Therefore, researchers have turned their attention to exploring alternative, non-biological explanations that might account for this phosphine presence. This unexplained anomaly raises critical questions about Venus's atmospheric chemistry and the planet's potential to harbor processes radically different from those we've seen elsewhere. Simultaneously, Venus's atmosphere continues to yield new insights, particularly regarding its complex and dynamic weather systems. The planet's thick, sulfuric acid-laden clouds give rise to intense and violent storms which share certain similarities with Earth's own weather patterns. Yet the origin and nature of these storms remain poorly understood. While Earth's weather is driven by the water cycle, evaporation, condensation, and precipitation, Venus's storms may be influenced by sulfuric acid instead, a chemical more commonly found in the planet's extreme clouds. These atmospheric phenomena on Venus not only deepen our curiosity about the planet itself, but also highlight the vast diversity of planetary environments within our own solar system, each offering unique challenges and opportunities for scientific exploration. As we turn our attention to the far reaches of our solar system and beyond, another mysterious class of celestial bodies captures our imagination: rogue planets. These are planets that wander freely through space, unanchored by the gravitational pull of any star. Their very existence is a profound departure from the conventional model of planetary systems. Rogue planets may form in the same manner as other planets, through the accretion of gas and dust around a young star. But at some point in their evolution, they are cast out, either by gravitational interactions with neighboring planets or by cosmic events such as supernovae. Without the warmth and light of a nearby star, these rogue worlds are usually frigid, drifting alone in the vast expanse of space. The size of rogue planets can vary dramatically, from small, Earth-sized bodies to colossal gas giants that dwarf Jupiter. Despite their lack of a solar source, the atmospheres of rogue planets can exhibit a fascinating range of behaviors. Some may harbor subsurface oceans kept warm by geothermal energy, while others may be locked in an icy, barren state with thick atmospheres that struggle to retain any significant heat. What is particularly intriguing about rogue planets is the possibility that, in the absence of a sun's light, their environments may remain static, with little to no seasonal variation. Without the ebb and flow of seasonal cycles, These planets may experience relatively unchanging conditions, raising interesting questions about their potential to support ecosystems or sustain life in ways we haven't yet imagined. Furthermore, rogue planets challenge our preconceived notions about planetary formation and behavior. Their solitary existence in the cosmos offers a unique perspective on the diversity of worlds that exist beyond the confines of our solar system. As astronomers continue to explore these enigmatic wanderers, they may reveal unexpected insights into the processes that govern planetary evolution and the potential for life on worlds that defy the conventional norms of planetary existence. Exploring such distant and mysterious worlds comes with its own set of monumental challenges, especially when it comes to studying exoplanets, planets orbiting stars beyond our own solar system. One of the most significant hurdles astronomers face is the vast distance between Earth and these faraway worlds. Many exoplanets are located light years away, and the light they emit is often faint, obscured by the brilliance of their parent stars. Detecting these faint signals requires an array of cutting-edge techniques and technologies. One of the most widely used methods is the transit technique, in which astronomers observe the dimming of a star's light as an exoplanet passes in front of it. This small dip in brightness can reveal crucial information about the size and atmospheric composition of the planet. However, this method relies on precise orbital alignment, which makes finding exoplanets a slow and meticulous process, requiring long periods of observation across many stars. Once an exoplanet is detected, another major challenge emerges: determining its atmospheric composition. Understanding the gases that make up an exoplanet's atmosphere is vital for assessing its potential habitability. To accomplish this, astronomers use a technique known as spectroscopy. By analyzing the starlight that filters through an exoplanet's atmosphere during a transit, scientists can identify the presence of specific gases. Certain elements, such as water vapor or carbon dioxide, absorb and emit light at characteristic wavelengths, providing valuable clues about the planet's environment. This technique opens up a tantalizing window into the conditions that exist on distant exoplanets, offering a glimpse into whether these worlds could potentially support life. The recent advancements in space technology, particularly the launch of next-generation instruments like the James Webb Space Telescope, have significantly accelerated the study of exoplanets. Webb's ability to observe in a range of wavelengths, from infrared to visible light, allows astronomers to gather unprecedented data about distant planets. This enhanced capability is revolutionizing our understanding of exoplanets, bringing us closer to answering the age-old question: are we truly alone in the universe? As technology continues to improve, the study of exoplanets promises to open up even more exciting possibilities, shedding light on the mysteries of the cosmos and helping us explore the potential for life on distant worlds. The study of planets, rogue or otherwise, remains an ongoing journey. As we venture further into space, the mysteries of distant worlds continue to unfold, reminding us of the limitless possibilities of exploration. The presence of phosphine on Venus, the complex weather systems of distant planets, and the intriguing potential of rogue planets each offer unique insights into the forces that shape our universe. With each new discovery, we move closer to understanding not only the nature of our neighboring planets, but also the broader cosmic environment in which we exist, constantly challenging and reshaping our view of the universe. International collaborations and research institutions play a critical role in tackling the profound challenges that the cosmos presents to humanity. By pooling their resources, knowledge, and expertise, these organizations have become indispensable in pushing the boundaries of our understanding. Astronomy, in particular, has benefited from such partnerships, with scientists and researchers working together to uncover the myriad secrets of the universe. With each breakthrough, the astronomical community steadily inches closer to unraveling the mysteries of distant exoplanets and celestial bodies, previously veiled in darkness. Among the most remarkable of these discoveries is the identification and study of dwarf planets, which have significantly expanded our understanding of the solar system's complexity. Bodies like Eris and Haumea have reshaped how we think about our cosmic neighborhood. For many years, Pluto reigned as the largest known object within this category. Yet, The discovery of Eris, followed by Haumea, has led to a reevaluation of what it means to be a planet. Eris, for instance, shares a similar size to Pluto but exceeds it in mass, suggesting that our solar system harbors a diverse range of celestial bodies that challenge our traditional definitions of planets. Eris is particularly captivating due to its surface, which is coated in methane ice. This frost indicates not just a frozen exterior, but hints at the possibility of ongoing geological activity beneath the surface. This discovery suggests that Eris could have an atmosphere, opening up new avenues of exploration for scientists. Haumea, on the other hand, presents a different set of curiosities. Its elongated shape, a result of rapid rotation, raises intriguing questions about its formation and the processes that shaped it. These two dwarf planets, along with others in the Kuiper Belt, offer unique insights into the forces that sculpt icy worlds in this distant region of our solar system. The study of these distant celestial bodies doesn't just answer questions about their individual characteristics. It also offers critical clues about the early solar system. Eris and Haumea, in particular, hold the potential to reveal key information about the conditions that existed when the planets were forming. By examining the composition and positions of these objects, scientists can infer details about the processes that led to the formation and migration of planets in our solar system. This deeper understanding could lead to improved models that explain how Earth and its neighboring planets evolved over billions of years, telling the intricate story of the solar system's origins. Moreover, the ongoing exploration of dwarf planets forces us to confront broader, more philosophical questions about how we categorize celestial bodies in the universe. The debate over the definition of a planet has ignited ongoing discussions among both scientists and educators. This evolving perspective encourages a more inclusive view of the cosmos, inviting us to rethink not only how we classify celestial objects, but also our place within this vast and intricate universe. As our understanding deepens, we are prompted to appreciate the complex web of objects that populate our solar system, from the familiar planets to the distant and enigmatic dwarf worlds. In the far reaches of the solar system, certain celestial bodies follow peculiar orbital patterns that challenge our understanding of gravity and motion. A prime example is Haumea, which resides in the Kuiper Belt and exhibits a highly elongated orbit, vastly different from the more circular orbits of the planets. This elongated orbit is likely a result of Haumea's rapid rotation, which gives it a rugby ball-like shape. The gravitational influence of other Kuiper Belt objects may further contribute to the fascinating behavior of Haumea's orbit. Another extraordinary example lies with the distant object Sedna, whose orbit is both tilted and elongated. Sedna's trajectory takes it far beyond the familiar confines of our solar system, sparking debates among scientists. Some theorists suggest that a hypothetical planet, sometimes called Planet 9, could be responsible for Sedna's strange orbit. The gravitational pull of this unseen planet might be pulling Sedna and other distant objects into these unusual trajectories. This idea is still speculative, but it raises important questions about the forces at play in the outer solar system. The concept of the Oort cloud, a vast spherical shell of icy bodies surrounding the solar system, has also generated considerable interest. Comets that originate from this region often follow highly irregular orbits, which take them deep into the inner solar system. Some scientists hypothesize that gravitational influences from passing stars or galactic tides could be disrupting the orbits of these comets, causing them to spiral inward toward the sun in a breathtaking display of celestial dynamics. These intricate interactions between gravity, motion, and the influence of distant stars are crucial for understanding the behavior of these far-flung objects. These unusual orbital patterns remind us that our solar system is far from the orderly system it might first appear to be. Each strange trajectory tells its own story, an ongoing narrative about the dynamic forces shaping our solar neighborhood. As we learn more about the mechanics behind these fascinating phenomena, we open the door to even more profound questions about the nature of space and the cosmos. What else lies beyond our current reach? What other extraordinary phenomena are waiting to be discovered? The recent surge in Mars exploration has reignited scientific interest in the possibility of extraterrestrial life, positioning the red planet as one of the most promising candidates for the search for life beyond Earth. Mars has long captivated researchers due to its striking similarities to Earth. However, recent technological advancements and exploration missions have revealed a much more complex picture of Mars's past and present. Evidence suggests that Mars once had liquid water on its surface, a key ingredient for life as we understand it, leading many to wonder whether microbial life may have once thrived there. Rovers like Perseverance have uncovered signs of ancient riverbeds and lake deposits, bolstering the theory that Mars was once a much more hospitable world. This discovery paints a picture of a planet that, billions of years ago, may have been capable of supporting life. But the findings do not end there. Organic molecules have also been detected in Martian soil, raising further questions about Mars's potential to have hosted life. While these molecules do not prove the existence of life, their presence indicates that the fundamental building blocks necessary for life were once available on Mars. As scientists continue to analyze these findings, new questions arise about the conditions that may have allowed life to exist on Mars, and why, if life ever existed, it appears to have vanished. Could Mars have once hosted microbial life that evolved in ways we have yet to understand? Could the potential for life still exist on Mars today, hiding beneath its surface, shielded from the harsh conditions above? The ongoing study of Mars offers a tantalizing glimpse into the possibilities of life beyond Earth, prompting scientists to think deeper about the nature of life in the universe and the potential for its existence on other worlds. Each new discovery about Mars, and indeed the entire solar system, underscores how much we have yet to learn about the cosmos. The ongoing exploration of these distant worlds reminds us that the story of the universe is far from finished. Every piece of new evidence, every breakthrough adds another chapter to a story that has just begun to unfold. And as we continue to ask these fundamental questions about our place in the universe, we find ourselves drawn ever further into the mysteries of space, forever seeking to understand the secrets of the stars. Moreover, scientists have turned their attention to the Martian atmosphere, where they've made a groundbreaking discovery. Trace gases, such as methane, which could potentially be produced by biological processes. On Earth, methane is a key indicator of microbial life. This tantalizing finding opens up a whole new realm of possibilities. Could microbial life still be thriving beneath the Martian surface, where the conditions may be more hospitable than on the planet's exposed surface? The discovery raises hopes that Mars, once thought to be barren, might still harbor life in some form. These small but profound clues fuel the drive for further exploration. As scientists investigate the Martian atmosphere and analyze its surface, they continue to search for definitive evidence that life, whether ancient or present, may have once existed or still exists on the red planet. Every mission, from rovers to orbiters, brings fresh data that allows researchers to piece together Mars' history and its potential to sustain life. This ongoing exploration has transformed Mars into a central focal point in the field of astrobiology, pushing the boundaries of what we understand about life in the universe. The implications extend beyond Mars itself. By studying this enigmatic neighbor, scientists are learning not just about the planet, but about the very nature of life itself. The search for signs of life on Mars challenges our understanding of where life can exist and what it might look like in environments that are radically different from Earth. This journey pushes us to reconsider the definition of life and to imagine the possibility that we might not be alone in the cosmos. And with each passing mission, the dream of answering the age-old question of whether we are the only sentient beings in the universe grows closer, perhaps just one mission away from discovery. In addition to Mars, asteroids and comets also hold vital information about the origins of our solar system. These cosmic remnants act as time capsules, offering glimpses into the distant past over 4 billion years ago when the solar system was in its infancy. These objects contain clues about the conditions that prevailed during the chaotic period when our planets were forming. The study of asteroids, primarily located in the asteroid belt between Mars and Jupiter, helps us understand the rocky remnants of the early solar system. These bodies are rich in minerals that were created during the initial stages of planetary formation, And by examining them, scientists gain a deeper understanding of the environment that shaped our solar system. Comets, on the other hand, are typically found in the outer regions of the solar system, in areas like the Kuiper Belt and the Oort cloud. Their icy compositions reveal the volatile compounds that were dispersed across the solar system during its early formation. Through the study of these bodies, researchers can also gain insights into the building blocks of planets. Comets, in particular, are believed to have delivered water and organic compounds to Earth, playing a crucial role in creating the conditions necessary for life to emerge. This connection between comets and the origins of life raises profound questions. Could similar processes have occurred elsewhere in the universe? Are the seeds of life scattered across distant exoplanets in other star systems? Recent missions targeting asteroids and comets, such as NASA's mission to asteroid Bennu, aim to collect samples and return them to Earth. By studying these samples, scientists hope to unravel the mysteries of our planet's formation and better understand the broader dynamics of planetary formation across the galaxy. Each discovery brings us one step closer to piecing together the story of how our solar system came into being, and perhaps to understanding the role of asteroids and comets in the larger picture of life's emergence in the universe. Turning our gaze to the distant reaches of the cosmos, astronomers have uncovered remarkable phenomena centered around supermassive black holes. These colossal objects, often millions or even billions of times the mass of our sun, are thought to reside at the heart of nearly every large galaxy. Despite their ubiquity, our understanding of these behemoths remains incomplete. Observations reveal that supermassive black holes exert an immense gravitational pull, capturing stars, gas clouds, and even light itself. As matter spirals into a black hole, it forms an accretion disk, which heats up to extreme temperatures, emitting X-rays and other forms of radiation. These energetic emissions make the centers of galaxies some of the brightest objects in the universe. Yet, despite the brilliance they produce, many aspects of supermassive black holes remain a mystery. One key question is how these giants form and grow. Some galaxies appear to host black holes much larger than expected based on the amount of surrounding matter. This discrepancy raises fascinating questions. Could these black holes have formed from the merging of smaller black holes, or did they grow rapidly through mechanisms like the direct collapse of massive gas clouds in the early universe? Another intriguing phenomenon is the presence of relativistic jets, streams of charged particles ejected from the poles of certain supermassive black holes at nearly the speed of light. These jets can extend vast distances into space, impacting the evolution of the host galaxy. Yet the exact mechanisms behind the formation of these jets remain elusive, and understanding their role could unlock even deeper mysteries about the complex relationship between black holes and their cosmic environments. Galactic collisions, among the most spectacular events in the universe, offer another window into the workings of cosmic forces. When two galaxies collide, they don't crash like solid objects. Instead, their vast clouds of gas, dust, and stars pass through one another, triggering intense gravitational interactions. These interactions can compress gas clouds, leading to areas of higher density where new stars can form. The compression of gas often results in the birth of new stars, which shine brightly for millions of years before exploding as supernovae, enriching the surrounding space with heavier elements. This process, known as stellar renaissance, can radically transform the galaxy in the aftermath of a collision, creating a burst of new stars and elements that enrich the cosmic landscape. However, galactic collisions are not without their quirks. One fascinating outcome of these cosmic encounters is the formation of tidal tails, long, elongated streams of gas and stars that trail off from the galaxies as they collide. These tidal forces can produce bizarre, unexpected shapes in the galaxies, and in some cases, these structures become active, star-forming regions. This unique phenomenon contributes to the ongoing evolution of the galaxies involved, highlighting the dynamic and ever-changing nature of the cosmos. As we explore these phenomena from the surface of Mars to the heart of colliding galaxies, we are constantly reminded of the vastness and complexity of the universe. Each discovery brings us closer to understanding the forces that shape the cosmos and the potential for life beyond Earth. The universe continues to reveal its secrets, and with each step forward, we broaden our understanding of the universe's incredible story. Gravitational chaos in the cosmos can lead to some extraordinary and awe-inspiring phenomena. Stars, once anchored within their galaxies, can be flung into the cold, dark vastness of intergalactic space. In contrast, other stars may find themselves drawn into the powerful gravitational embrace of a newly formed galaxy. These cosmic collisions bring not only destruction, but also a creative force, one that can disrupt existing star systems in the most unpredictable ways. Some stars may lose their orbits altogether, spinning out of control, while others may merge, giving rise to the possibility of binary star systems or, in more extreme cases, black holes. These dynamic interactions unfold like a cosmic tapestry, weaving the story of the universe's constant transformation and regeneration. The collision of galaxies is not simply an event of destruction. Instead, it acts as a catalyst for creation, a vibrant force that reshapes the cosmos. Amidst this cosmic chaos, we encounter one of the most mysterious and intriguing phenomena in modern astronomy, the Great Attractor. This gravitational anomaly, located in the direction of the Centaurus constellation, about 100 million light-years away from Earth, exerts an immense force on the galaxies in our local supercluster, drawing them inexorably toward it. Imagine, if you will, a colossal cosmic spider whose web is made of galaxies, slowly drawing them toward its center. Though the Great Attractor itself is not directly visible, obscured by intervening galaxies and cosmic dust, its existence is inferred through the peculiar motion of galaxies. These galaxies are not moving randomly. They exhibit a distinct drift toward this invisible gravitational well. This discovery has forced astronomers to reconsider the ways in which galaxies cluster and interact across the vastness of space. The significance of the Great Attractor extends beyond just its gravitational pull. It offers insights into the large-scale structure of the universe, revealing how gravity shapes the distribution of galaxies and the elusive presence of dark matter. It also raises profound questions about the expansion of the universe itself. As the universe continues to stretch outward, the forces of gravity at play, like those exerted by the Great Attractor, provide a window into how gravity operates on a universal scale. Unraveling the mysteries of this cosmic force offers us deeper insights into the composition of the universe and the fundamental forces that bind everything together. The study of the Great Attractor not only enhances our understanding of cosmic structure, but also pushes the boundaries of what we know about the invisible forces that govern the motions of celestial bodies. Each new revelation brings us closer to understanding the very fabric of the universe, peeling back the layers of cosmic history and uncovering the hidden truths that govern our existence. Equally crucial to our understanding of the cosmos is the rotation of galaxies, a phenomenon that has become a cornerstone in the study of dark matter. When astronomers examine galaxies, they often encounter a puzzling observation. The stars in the outer regions of galaxies rotate at speeds that defy explanation. According to the laws of physics, particularly Newton's law of gravity, we would expect the stars on the outer edges of a galaxy to move more slowly, much like how planets farther from the sun take longer to complete their orbits. But this is not what observations reveal. Many galaxies, including our own Milky Way, exhibit what is known as a flat rotation curve. This means that the rotational speed of stars remains roughly constant, even at great distances from the galaxy's center. If we only consider the visible matter, such as stars and gas, the expected rotational speeds should decrease as the distance from the center increases. The fact that this doesn't happen suggests the presence of something unseen, something that exerts a gravitational influence on the visible matter, dark matter. Dark matter, as it is called, is thought to be a form of matter that does not emit, absorb, or reflect light. It is invisible to traditional forms of detection, and yet its presence is inferred through its gravitational effects on the visible universe. Its influence is particularly noticeable in the way galaxies rotate. By incorporating dark matter into models of galaxy structure, astronomers can more accurately represent the mass distribution within galaxies, resolving the mystery of the flat rotation curves. Dark matter does more than explain the rotation of galaxies. It also plays a significant role in the formation and structure of larger cosmic objects, such as galaxy clusters. It is integral to our understanding of the formation of the universe itself. Through studying galaxies and their peculiar motions, astrophysicists gather vital clues that help us understand the true nature of dark matter, a mysterious substance that dominates the mass-energy balance of the universe. This enigma continues to captivate scientists, driving the future of cosmological research and shaping our quest to comprehend the vastness of the cosmos. Amidst the complexity of cosmic interactions lies the creation of stars, an event that takes place in vast regions of space known as stellar nurseries, or molecular clouds. These stellar nurseries are cold, dense regions composed primarily of hydrogen gas, along with other elements. Here, gravity plays a crucial role, drawing the gas and dust together to form clumps that eventually collapse. As these clumps condense, nuclear fusion begins, giving birth to new stars. The entire process, from the collapse of gas clouds to the birth of stars, is a beautiful and natural cycle that contributes to the ever-changing life of galaxies. What makes stellar nurseries particularly fascinating, however, is their ability to create unexpected anomalies within galaxies. When a new star forms, it generates strong stellar winds and radiation that can push away surrounding material, clearing out large regions of the nursery. If multiple stars form in close proximity to one another, their collective energy can trigger supernova explosions. These explosive events, in turn, scatter heavier elements across space while also compressing nearby gas and dust. This compression can spark the formation of even more stars, creating a feedback loop of star formation that can lead to irregular patterns across a galaxy. These processes often result in the formation of star clusters or even chaotic regions where star formation occurs in unexpected ways. The interaction between stars, gas, and dust in these nurseries illustrates the dynamic and ever-evolving nature of galaxies, a testament to the incredible forces at work in the universe. Through the study of these processes, from the dramatic collisions of galaxies to the mysterious effects of dark matter and the birth of new stars, we gain a deeper understanding of the cosmos. The universe is not a static entity, but a constantly evolving system, shaped by forces both visible and invisible, known and unknown. Each discovery adds another layer to our understanding of this grand and awe-inspiring universe. Moreover, some stellar nurseries possess an unexpectedly vivid and striking appearance, a result of the energetic processes unfolding within them. One striking phenomenon is the light emitted by young, nascent stars. This light heats the surrounding clouds of dust, causing them to glow with radiation in the infrared spectrum. As a result, these glowing regions can be detected across vast distances, offering a beacon of where stars are actively forming. The various hues that emerge from these regions are not mere visual curiosities. They reveal critical information to astronomers. The contrasting shades of color can tell us about the age of the stars, the dynamics of their formation, and the conditions within these celestial clouds. Stellar nurseries, therefore, are far from being passive regions. Rather, they are active and dynamic, shaping the very structure of galaxies. They illustrate the intricate balance between the birth and death of stars. These constant processes, accompanied by their occasional anomalies, paint a picture of an ever-evolving cosmos. Through the apparent chaos of creation and destruction, we can see beauty unfolding. This ongoing cosmic dance continues to captivate both scientists and stargazers alike, revealing the delicate and intricate tapestry of the universe. As we shift our focus to a more puzzling aspect of the cosmos, the phenomenon of missing dark matter challenges our understanding of the universe's structure. Observations show that while most galaxies are assumed to contain substantial amounts of dark matter, an elusive, invisible substance that exerts gravitational influence, some galaxies appear to lack it entirely. This raises profound questions about the formation and evolution of galaxies over cosmic time. One of the most intriguing examples of this oddity can be found in dwarf galaxies, which are smaller and dimmer than their larger counterparts. These dwarf galaxies often exhibit an unexpected distribution of visible matter and unusual velocity patterns. These irregularities suggest that they might not contain the vast quantities of dark matter typically associated with galaxies of their size. Researchers have begun to propose that these galaxies may have followed a different path in their formation, possibly due to interactions with larger galaxies or the influence of their environment in the cosmic neighborhood. The implications of these findings extend far beyond the mere absence of dark matter in certain galaxies. By studying these peculiar galaxies, scientists may gain valuable insight into the very nature of dark matter itself. Understanding why these galaxies formed without the expected dark matter could help refine current models of dark matter's role in galaxy formation and structure. Moreover, these discoveries challenge our existing theories, pushing astronomers to reconsider the fundamental mechanics of the universe. Each discovery brings us closer to understanding the cosmic evolution that governs the universe, inviting us to explore the many mysteries that lie beyond our observable realm. When we turn our gaze toward the universe's vast expanse, we encounter structures of staggering scale. The largest known cosmic entities stretch across distances so immense that it's almost beyond comprehension. Among these colossal formations are galaxy superclusters, vast groupings of galaxies, and immense cosmic filaments that form what is known as the cosmic web. One of the most remarkable of these superclusters is the Hercules Corona Borealis Great Wall, which is so enormous that it spans approximately 10 billion light years. These superclusters and filaments are not random. They are intricately woven structures, crafted by the gravitational forces that govern the universe. The process of uncovering these monumental formations began with the earliest efforts of astronomers mapping the positions of galaxies and their clustering patterns. Initially, early telescopes allowed for the identification of galaxies in clusters, but it wasn't until the advent of more advanced technology, such as radio telescopes and space-based observatories, that astronomers were able to detect much fainter objects, leading to the discovery of these massive cosmic structures. Optical surveys, such as the Sloan Digital Sky Survey, have played a pivotal role in unveiling the large-scale structure of the universe. Over time, these surveys revealed that galaxies are not distributed evenly throughout space. Instead, they form long, interconnected strands, filaments, and clusters with vast voids between them. This realization reshaped our understanding of the universe, showing us that our cosmos is far more structured than previously thought. In more recent studies, techniques like gravitational lensing have added yet another layer to our understanding of the universe's architecture. Gravitational lensing occurs when the gravity of a massive object distorts the light from distant galaxies, allowing scientists to observe galaxies and map the distribution of dark matter in ways previously unimaginable. By studying the interaction of light and gravity, researchers have uncovered intricate webs of galaxies that confirm the existence of the cosmic web theory. The study of these massive structures is more than just an effort to identify the largest entities in the universe. It's an investigation into the underlying processes that dictate the formation of galaxies and the overall dynamics of the universe itself. These vast formations tell a story, one of the birth and evolution of galaxies, the movement and influence of dark matter, and the overall progression of the cosmos. In this sense, our quest to understand these structures transcends the scientific. It becomes profoundly philosophical, as we seek to understand the very nature of the universe and our place within it. Magnetic fields, too, offer a fascinating glimpse into the mechanics of galaxies and their evolution. These invisible fields, which can span across vast distances, arise from the movement of charged particles, such as electrons, within galaxies. While we tend to think of magnets in everyday terms, such as the magnet on a refrigerator, galactic magnetic fields operate on a far grander scale, influencing the behavior of cosmic dust, gas, and even the formation of stars. One of the primary areas where magnetic fields have a significant impact is in the dynamics of galaxy formation and evolution. These magnetic fields affect the motion of ionized gas, which constitutes a large portion of a galaxy's mass. As charged particles move along magnetic field lines, they lose energy, which can alter the density and temperature of the gas. These changes, in turn, can influence the rate at which stars form. The interaction between magnetic fields and interstellar gas provides valuable insights into why some galaxies thrive, bursting with new stars while others remain dormant. In some, these magnetic fields are not merely a curiosity. They are an integral part of the cosmic machinery, shaping the formation and behavior of galaxies across the universe. Just as with dark matter and large-scale cosmic structures, magnetic fields offer another layer to our understanding of the intricate, ever-evolving universe we inhabit. Magnetic fields, though invisible, are powerful forces that govern many aspects of the cosmos. Their influence extends far beyond the boundaries of the galaxies, playing a significant role in shaping phenomena such as cosmic rays, a high-energy stream of particles originating from the most explosive and energetic events in the universe. These particles are born in stellar explosions or other violent cosmic processes and travel vast distances through space. However, their trajectories are not solely determined by the forces of gravity or inertia. Instead, magnetic fields embedded within galaxies alter their paths in complex and often unpredictable ways. As these cosmic rays journey through the universe, they encounter magnetic fields that bend, twist, and deflect their course. This interference results in subtle but significant changes to how we observe cosmic rays on Earth. Their intensity and distribution, key data points for astronomers, can be dramatically affected by these fields, leading to shifts that provide a richer and more intricate view of the galactic environment. Rather than being passive background players in the cosmic drama, magnetic fields are shown to be active participants, profoundly influencing everything from the movement of high-energy particles to the broader dynamics of galaxies. Researchers are now leveraging the most advanced observational tools and cutting-edge simulations to explore and better understand these cosmic magnetic forces. As we deepen our understanding of galactic dynamics, it is becoming clear that these invisible forces are not just incidental, but vital components of the universe's grand design. They affect everything, from the formation of stars to the behavior of cosmic rays, and may hold the key to unlocking many of the mysteries of the cosmos. With each new discovery, the magnetic fields that govern the universe reveal themselves as even more crucial and mysterious, challenging our perceptions and pushing the boundaries of our understanding. In addition to magnetic fields, another essential structure in the universe's architecture are cosmic filaments. These colossal threads, stretching across hundreds of millions of light years, form the scaffolding for galaxy formation and distribution. Comprised primarily of galaxies, gas, and dark matter, cosmic filaments make up the cosmic web that defines the large-scale structure of the universe. Within this web, dense regions filled with galaxies and clusters are connected by these vast filaments, while enormous voids stretch between them. The formation of these cosmic filaments is a result of gravitational forces at work, acting on matter as the universe expanded following the Big Bang. In the early universe, regions of higher density attracted more matter, eventually causing the formation of long, slender structures. This process not only determined the location of galaxies, but also influenced the evolution of the cosmic environment itself. Galaxies within these filaments are more likely to interact, merge, and grow, shaping the structures we observe in the present day. Moreover, cosmic filaments are crucial in facilitating the flow of gas and dark matter throughout the universe. Acting as channels, they funnel gas into the centers of galaxy clusters, triggering star formation and fueling the growth of galaxies. This ongoing influx of material drives a variety of cosmic processes, including the creation of new stars and the recycling of matter back into the cosmic ecosystem. By studying these filaments, we gain deeper insight into how galaxies evolve and how they continue to shape and influence the broader structure of the universe. These filaments are not merely physical features of the cosmos, but the guiding pathways of cosmic evolution. Supernovae, the explosive deaths of massive stars, represent another key event in the ongoing story of the universe. When these stellar giants reach the end of their life cycles, they erupt in a cataclysmic explosion, releasing an immense amount of energy in a brief, intense moment. However, the impact of a supernova extends far beyond the immediate blast. The shockwaves created by the explosion ripple outward, affecting surrounding galaxies and triggering a series of complex reactions in the cosmic environment. One of the most remarkable outcomes of a supernova explosion is its ability to foster new star formation. The immense force of the explosion compresses nearby gas and dust, causing it to collapse under its own gravity and potentially ignite the birth of new stars. This process often leads to the creation of fresh, luminous stellar populations that enrich the galaxy over time. These newborn stars are not simply new additions to the stellar roster, but are critical in shaping the evolution of their galaxy, influencing its appearance, structure, and future trajectory. Supernovae also play an essential role in the broader chemical evolution of the universe. As the stars explode, they scatter heavy elements forged in their cores, into the surrounding interstellar medium. These elements, essential for the formation of planets and life, are reintroduced into space, enriching the gas clouds and ensuring the continuous cycling of materials necessary for the creation of new cosmic structures. In this way, each supernova acts as a cosmic recycling center, ensuring that the building blocks of life and the universe's complexity are always available for the next generation of stars, planets, and galaxies. In every corner of the universe, from the magnetic fields that shape cosmic rays, to the filaments that guide galaxies, to the explosive events of supernovae, the forces at work are intricately connected. Each of these elements plays a crucial role in the cosmic dance, one that has unfolded over billions of years. By examining these phenomena, scientists not only gain a better understanding of the universe's past, but also glimpse the future of galactic and stellar evolution. As we continue to explore the cosmic tapestry, we uncover deeper insights into the forces that have sculpted the universe and the mysterious processes that govern its evolution. The remnants of a supernova carry with them more than just the violent remnants of a star's death. They hold the power to influence the very dynamics of their host galaxies. A supernova's explosive energy can send shockwaves through space, altering the motion of nearby stars and gas clouds. Over time, these shifts can have profound effects on the orbits of these cosmic bodies, forcing them to follow new paths. When multiple supernovae occur within the same region, their combined impact can reshape the surrounding area of the galaxy, contributing to phenomena like galactic winds, which in turn drive the ongoing evolution of galaxies across vast cosmic timescales. The intricate cycle of birth, death, and rebirth that stars undergo is far from an isolated process. It is a fundamental force that shapes the universe in ways that are often far more profound than we might realize. These stellar cycles are not merely accidents of nature, but a powerful force in the dynamic tapestry of the cosmos. The role of early astronomers in deciphering the mysteries of the universe was equally transformative. Long before the advent of advanced telescopes and space exploration, these ancient observers played a crucial part in laying the foundations of modern astrophysics. They didn't have the tools we rely on today, yet their painstaking observations and meticulous recordings of the stars, planets, and other celestial bodies helped form the early understanding of the heavens. These astronomers noticed irregularities in the motion of the planets, strange, unpredictable shifts that didn't fit with the established patterns of the stars. They recognized that certain celestial bodies appeared to move erratically, as though they were wandering against the backdrop of the fixed stars. These anomalies sparked curiosity and prompted deep questions about the nature of the cosmos. It was this relentless pursuit of knowledge that led to groundbreaking discoveries. The ancient Greeks, including philosophers like Ptolemy and Aristotle, were among the first to attempt explanations for these celestial quirks. One of the most puzzling phenomena was retrograde motion, the apparent backward motion of planets in the night sky. In their quest to understand this, Ptolemy developed the geocentric model of the universe, which proposed that Earth was the center of all things, with the planets and stars orbiting around it. To account for the erratic motion of the planets, he introduced the idea of epicycles, small circular orbits within larger orbits. While this model was ultimately proven wrong, it was an early attempt to grapple with the complexity of the universe. It demonstrated humanity's willingness to engage with difficult questions and paved the way for future refinements in our understanding of the cosmos. As the centuries passed and technology advanced, astronomers began to develop tools that would forever alter the way we viewed the heavens. With the invention of the telescope in the 17th century, figures like Galileo Galilei transformed the study of the stars. Through his observations, Galileo uncovered astonishing new phenomena. He saw the spots on the sun, the moons orbiting Jupiter, and the phases of Venus, all of which provided crucial evidence for the heliocentric theory proposed by Copernicus. This model placed the sun at the center of our solar system rather than the Earth, and Galileo's work offered solid proof that the celestial anomalies were not just imperfections in the universe, but integral parts of a much grander cosmic order. The work of these early astronomers ignited a chain of discoveries that would continue to unravel the mysteries of the universe. With each passing century, technological advancements in telescopes and instruments opened new doors to exploration. As astronomers turned their attention beyond our solar system, they discovered new and often puzzling phenomena in distant galaxies. The detection of supernovae, the identification of black holes, and the discovery of cosmic microwave background radiation all revealed deeper layers of complexity within the universe. These findings not only illuminated our understanding of the origins of the universe, but also hinted at the astonishing nature of the cosmos, its vastness, its intricacies, and its ongoing evolution. The insights gained from these celestial anomalies would ultimately lead to some of the most groundbreaking theories of the 20th century, particularly the work of Albert Einstein. Before his contributions, scientists viewed space and time as fixed and unchanging, like the immutable laws of nature. But Einstein's theories shattered that perception. He proposed that space and time were not separate entities, but rather interconnected in a single fabric known as space-time. This revolutionary concept changed the course of physics, as it showed that massive objects like stars and planets could warp space-time, affecting the motion of other objects. His general theory of relativity, published in 1916, revealed that gravity was not a mere force acting at a distance, as Newton had proposed, but rather a curvature in space-time caused by mass. This radical shift in understanding allowed scientists to explain phenomena that had previously been inexplicable. The orbits of planets, the bending of light around massive objects, and the very expansion of the universe could now be described through the lens of general relativity. One of the most compelling confirmations of Einstein's theories came in the form of observations made during solar eclipses, where light from distant stars appeared to bend as it passed near the sun, just as Einstein had predicted. These observations provided early experimental support for his ideas and sparked a wave of excitement in the scientific community. Even more astonishing was the realization that general relativity was the foundation upon which modern cosmology was built. It opened the door to theories about the nature of the universe that were previously unimaginable. Concepts like black holes, cosmic inflation, and the Big Bang. Before Einstein, the universe was thought to be static and unchanging, a view that had persisted for centuries. However, his work revolutionized our understanding, revealing a dynamic, ever-evolving cosmos. The universe, it turns out, was not a fixed, eternal entity, but rather a constantly expanding and shifting system, governed by the very fabric of space-time itself. Einstein's insights set the stage for countless discoveries in modern astrophysics, leading to a deeper and more nuanced understanding of the universe's origins, its structure, and its future. The theories he introduced continue to shape our exploration of space, guiding the development of new technologies and the discovery of new phenomena. His work exemplifies the power of scientific inquiry, how one mind, in challenging conventional wisdom, can unlock the deepest mysteries of the universe and change the course of human understanding forever. Einstein's theories continue to shape and guide research across the realms of cosmology and astronomy. They serve as the foundation of our exploration into dark energy and dark matter, two of the most dominant yet elusive components of the universe. These mysterious elements exert an immense influence on the cosmos, yet their true nature remains largely unknown. Einstein's legacy, however, extends far beyond the introduction of groundbreaking ideas. It represents a profound transformation in how we understand our place in the vast expanse of space and the fundamental laws that govern our reality. His theories have not only inspired endless scientific inquiry, but also pushed us to ask deeper, more challenging questions about existence itself. As we delve further into the cosmos, we are reminded that the universe is not simply a place of endless stars and galaxies, but a complex system waiting to be understood. Theoretical frameworks, such as those pioneered by Einstein, continue to inspire the next generation of scientists, inviting us to look beyond the familiar and embrace the unknown. His work serves as a catalyst for further exploration, encouraging new lines of questioning that challenge the very fabric of reality. Throughout history, women have made extraordinary contributions to astrophysics, often in the face of significant societal obstacles. These women defied the odds to leave an indelible mark on the field, and their work has shaped the way we understand the universe. One of the most notable figures in early 20th century astrophysics was Henrietta Swan Leavitt, a pioneering astronomer at Harvard University. Leavitt's groundbreaking study of variable stars, particularly Cepheid variables, led to the discovery of a crucial relationship between a star's brightness and its periodicity. This discovery provided a key method for measuring cosmic distances, helping astronomers determine the vast scale of the universe for the first time. Leavitt's work unlocked the ability to chart the distances between stars and galaxies, dramatically expanding our understanding of the cosmos. Another remarkable woman whose work transformed our understanding of the universe was Vera Rubin. In the mid-20th century, Rubin conducted research that provided compelling evidence for the existence of dark matter. By observing the rotation curves of spiral galaxies, she discovered that the outer regions of these galaxies were rotating much faster than conventional physics could explain. This observation was pivotal. It indicated the presence of unseen mass, which we now call dark matter, exerting a gravitational influence. Rubin's findings revolutionized our understanding of the universe's composition, raising questions about the unseen forces that shape cosmic structures and prompting a deeper investigation into the nature of dark matter. Then there is Jocelyn Bell Burnell, whose groundbreaking discovery in the 1960s changed the course of astrophysical research. As a graduate student at the University of Cambridge, Burnell discovered the first pulsar, a highly magnetized, rapidly rotating neutron star that emits beams of electromagnetic radiation. This discovery was monumental, not only enhancing our understanding of stellar evolution, but also igniting a new field of study within astrophysics. Despite initially receiving limited recognition, the pulsar's discovery paved the way for subsequent breakthroughs and opened doors to further exploration into the nature of neutron stars and the behavior of matter under extreme conditions. Burnell's work exemplifies how one individual's contribution can ripple through the scientific community, changing the course of research for generations to come. The influence of these women goes far beyond their individual discoveries. Their work has inspired generations of researchers and has played a crucial role in advancing diversity within the scientific community. Today, women continue to lead groundbreaking research in astrophysics, ensuring that the field remains vibrant, dynamic, and inclusive. These pioneers have shown that the mysteries of the universe are best understood when a variety of voices come together, each contributing unique perspectives to the conversation. The invention of the telescope in the early 17th century marked a revolutionary moment in our quest to understand the universe. Before this technological breakthrough, humanity's perception of the cosmos was confined to the limitations of the naked eye. Our understanding of the heavens was largely based on observations made from Earth, relying on crude methods of stargazing and rudimentary instruments. The telescope, however, opened an entirely new window onto the universe, offering a glimpse of celestial bodies in unprecedented detail. One of the earliest and most influential proponents of the telescope was the Italian scientist Galileo Galilei. Armed with a handmade telescope, Galileo made a series of groundbreaking observations, including the discovery of Jupiter's moons. This revelation was crucial because it demonstrated that not all celestial bodies orbited Earth, directly challenging the centuries-old belief in a geocentric universe, a model that placed Earth at the center of all things. Galileo's observations laid the groundwork for a heliocentric understanding of the solar system, where the Sun, not Earth, was the center of planetary motion. These discoveries, though controversial at the time, set the stage for a new era in our understanding of the cosmos. As telescope technology advanced over the centuries, so did our understanding of space. Early telescopic observations revealed the intricate features of the Moon, the swirling rings of Saturn, and the complex structures of distant galaxies. With improved lenses and magnification, astronomers began to uncover the true scale and complexity of the universe. The telescope allowed us to observe nebulae, supernovae, and the dynamic behavior of distant stars, each new discovery building on the last and expanding our knowledge of stellar life cycles. Today, modern telescopes, both ground-based and space-based, have opened up new frontiers in astronomy, enabling us to study phenomena like dark matter, dark energy, and the very fabric of space-time itself. These instruments continue to push the boundaries of what is possible, offering us a deeper understanding of the universe and our place within it. As we peer deeper into space, we are constantly reminded of how far we've come and how much more there is yet to discover. In the end, the history of astronomy is a story of curiosity, perseverance, and discovery. From the theoretical foundations laid by Einstein to the groundbreaking contributions of women like Leavitt, Rubin, and Bell Burnell, our understanding of the universe has been shaped by a diverse array of thinkers and innovators. The invention of the telescope, in particular, remains one of the most transformative events in the history of science, allowing us to transcend the limitations of our senses and uncover the mysteries of the cosmos. As we continue to explore the universe, we stand on the shoulders of those who came before us, inspired by their discoveries and motivated by the countless questions that remain unanswered. The journey of exploration, it seems, is far from over. Powerful observatories such as the Hubble Space Telescope provide us with an unprecedented view into the distant corners of the universe. With their help, we can gaze billions of light years away, peering into the depths of space, an endeavor that has fundamentally changed our understanding of the cosmos. The capabilities of these telescopes continue to be vital in the search for knowledge, offering us a glimpse into the infinite unknown. They are our window into a universe filled with mysteries, encouraging exploration in ways that, just a few decades ago, seemed beyond imagination. In this grand journey of discovery, one figure stands out: Carl Sagan. Renowned for his ability to translate complex scientific concepts into captivating narratives, Sagan became a guiding light for the public's fascination with the universe. He wasn't just a scientist, he was a communicator who brought the universe to the masses. Through his iconic television series Cosmos, which first aired in 1980, he introduced audiences to the wonders of space, including the enigmatic phenomena of black holes, quasars, and distant celestial anomalies. His ability to combine stunning visuals with accessible language made the vast and complex universe feel not just understandable but awe-inspiring. Sagan's approach was rooted in storytelling, and he used vivid metaphors to simplify even the most abstract ideas. For instance, he compared the behavior of light around black holes to water spiraling down a drain, an analogy so simple yet powerful that it allowed the audience to visualize something as unfathomable as the bending of space-time. Through such creative metaphors, he turned science into an experience that felt relatable, engaging, and above all, thought-provoking. Sagan's impact wasn't confined to television. His books, such as Pale Blue Dot and Contact, blended scientific inquiry with deep philosophical reflection, urging readers to grapple with the vastness of the universe and our fleeting place within it. Through his written works, he extended his reach, touching the minds of millions, prompting them to ponder not only the mysteries of the cosmos, but the very nature of human existence. His ability to merge narrative with scientific education was transformative, and it sparked a curiosity that led many to seek further knowledge about the universe and our connection to it. At the core of Sagan's legacy was his ability to spark wonder. He didn't just inform, he inspired. By popularizing the concept of space anomalies and exploring them with both intellectual rigor and poetic wonder, he helped ignite a deep-seated curiosity in people around the world. Through Sagan, space exploration became something more than an academic pursuit. It became a profound journey into the unknown, a quest not just for knowledge, but for a greater understanding of who we are and why we are here. His work continues to influence generations of scientists, writers, and dreamers, fostering a culture of exploration that thrives today. Sagan's contributions were made possible in part by the era of the space race, a defining period between the late 1950s and early 1970s that reshaped humanity's understanding of the cosmos. This intense competition between the United States and the Soviet Union was driven by a fierce desire to reach monumental milestones in space exploration. Both nations poured enormous resources into advancing technology, eager to surpass each other in their quest to conquer the final frontier. It was during this time that breakthroughs in space technology allowed for the observation of space anomalies in ways that had never been possible before. The launch of Sputnik in 1957, the first artificial satellite, marked a pivotal moment in the race. It not only demonstrated the potential of space exploration, but also gave scientists valuable data on cosmic radiation and the Earth's magnetosphere, laying the groundwork for more advanced observations. This newfound capability to explore space opened doors to studying the phenomena that had long captivated the imaginations of scientists and the public alike, from black holes to distant galaxies. The development of powerful instruments, including advanced telescopes like the Hubble Space Telescope, brought these anomalies into sharper focus. The Hubble allowed scientists to observe the cosmos with unprecedented clarity, bringing distant black holes, pulsars, and other space phenomena into view. The space race, though defined by rivalry, was also an era of remarkable collaboration, especially as it became evident that the limitations of national resources could only take us so far. Projects like the International Space Station became symbols of global cooperation, with scientists from all over the world pooling their knowledge and expertise to push the boundaries of what was known about the universe. Through international collaborations, researchers made significant strides in understanding dark matter, cosmic background radiation, and other mysterious aspects of the cosmos. These discoveries provided essential context for understanding the broader workings of the universe and its vast, complex nature. They have shaped our current understanding of the cosmos, highlighting the profound mysteries that continue to challenge our perceptions of reality. The space race was more than a competition. It was a catalyst for change. It ignited an urgency in space research that drove technological innovation and sparked a revolution in our understanding of space anomalies. The discoveries made during this era laid the foundation for the modern era of space exploration, and their impact continues to reverberate today. What began as a geopolitical race has become a global pursuit of knowledge, revealing the intricacies of space and reminding us of the vast unknowns that remain, waiting to be explored. Today, the work of pioneers like Carl Sagan and the monumental achievements of the space race still resonate. We continue to explore the universe, reaching deeper into space with more sophisticated instruments and more collaborative efforts than ever before. The space anomalies that once seemed beyond comprehension are now subjects of intense study, and each new discovery challenges our understanding of the universe and our place within it. Through the lens of telescopes like Hubble and the legacy of figures like Sagan, humanity's exploration of the cosmos remains as captivating, mysterious, and inspiring as ever. Ancient civilizations, driven by a blend of practical necessity, spiritual beliefs, and a desire to understand their place in the vast world around them, made profound contributions to our understanding of the stars. These early peoples, spanning from the Babylonians and Egyptians to the Mayans and Greeks, were not just observing the sky for the sake of curiosity. They were navigating their existence, both literally and symbolically, through celestial patterns. The Babylonians, with their meticulous records of star movements, laid the foundation for the earliest astronomical systems. Their observations contributed significantly to the mathematical models of the stars and planets that would later influence the Greeks, and much later the development of Western astronomy. The Egyptians, too, made astronomy a crucial part of their culture. For them, the stars were not mere points of light in the night sky. They were deeply intertwined with their mythology, religion, and monumental architecture. The alignment of the Great Pyramids with specific star constellations, like Orion, was no accident. The Egyptians associated stars like Sirius with the annual flooding of the Nile, an event that was vital for their agriculture. This connection between celestial bodies and earthly events highlights their extraordinary ability to understand and utilize the heavens for practical purposes. The Egyptian solar calendar, one of the most precise of its time, was based on a solar year of 365 days, demonstrating their remarkable understanding of astronomical phenomena. In the Americas, the Mayans also left behind a legacy of astronomical sophistication. Their calendar systems, which were intricately tied to celestial observations, were used not only to mark time, but also to guide agricultural practices and religious ceremonies. They tracked the movements of Venus, associating its appearance with both war and agriculture, an example of how they used the stars to shape their worldview and societal rhythms. These ancient civilizations not only enhanced their understanding of the universe, but also laid the groundwork for modern astronomy, offering a testament to human curiosity and our unceasing quest to unravel the mysteries of the cosmos. Fast forward to the modern era, and our exploration of space has transformed from myth and observation into actual missions that send spacecraft beyond the boundaries of Earth. One of the most groundbreaking programs in the history of space exploration is NASA's Voyager missions, launched in the late 1970s. Voyager 1 and Voyager 2 embarked on a journey through the outer solar system, performing flybys of Jupiter, Saturn, Uranus, and Neptune. Their images and data, which included revelations about the atmospheres, magnetic fields, and moons of these gas giants, reshaped our understanding of the outer reaches of our solar system. These missions provided a glimpse into the complexity of the dynamic systems that exist beyond Earth's orbit, sparking renewed interest in the far corners of space. Another pioneering mission, the Galileo spacecraft, launched in the late 1980s, focused its attention on Jupiter, the largest planet in our solar system. Galileo's extensive observations not only deepened our knowledge of Jupiter itself, but it also revealed fascinating details about its moons, especially Europa. Europa, a moon of Jupiter, is believed to harbor a subsurface ocean beneath its icy crust. This discovery has ignited discussions about the possibility of life beyond Earth, as Europa might contain the right conditions to support life as we know it. The Galileo mission, along with others like it, has reshaped our understanding of the potential for life elsewhere in our solar system. Alongside these missions, NASA's Mars rovers, such as Spirit, Opportunity, and Curiosity, have profoundly altered our views of the red planet. These rovers, equipped with tools to conduct on-site analyses and observations, have delivered critical insights into Mars's geological past, revealing evidence of ancient water flows and the planet's complex history. Curiosity's discovery of organic molecules in Martian soil, for example, has sparked ongoing debates about the possibility of past life on Mars. These findings make the Mars missions some of the most crucial in our search for answers about our neighboring planet and its potential to host life. In addition to these landmark missions, the Juno spacecraft, which has been orbiting Jupiter since 2016, continues to expand our knowledge of the gas giant. Juno's advanced instruments have provided detailed maps of Jupiter's gravitational and magnetic fields, while also probing its atmospheric structure and complex weather systems. Each mission, from the Voyagers to Juno, adds another puzzle piece to our understanding of distant worlds and, by extension, the origins of our own planet and its place within the cosmos. As we venture further into space, our exploration is not just about uncovering the secrets of faraway planets, but also about pushing the boundaries of what we know about the universe itself. Each mission expands our horizons, offering new insights into the nature of the universe and the fundamental forces that govern it. But perhaps no field has had as profound an impact on our understanding of the cosmos as quantum mechanics. Quantum mechanics, the branch of physics that studies the behavior of particles at the smallest scales, has revolutionized our approach to astrophysics. It has introduced a level of complexity and unpredictability that classical physics could never have explained. In the quantum realm, particles exhibit dual characteristics, behaving both like particles and like waves. This duality has profound implications for our understanding of the universe, influencing everything from the formation of stars to the behavior of black holes. One of the most significant areas where quantum mechanics has impacted astrophysics is in the study of stellar evolution. Stars, as we know, generate energy through nuclear fusion, a process that occurs when hydrogen nuclei fuse together to form helium. Quantum tunneling, a phenomenon where particles pass through barriers they would not be able to cross under classical physics, plays a key role in this process. Without quantum tunneling, stars would not be able to generate the energy necessary to sustain their long life cycles. This insight has altered our understanding of how stars are born, live, and die, and has deepened our knowledge of how the elements that make up the universe are created. In conclusion, the contributions of ancient civilizations, the groundbreaking space missions of modern science, and the profound insights offered by quantum mechanics all form a rich tapestry that continues to evolve. Each discovery, each new mission, and each step forward in our understanding of the cosmos offers us a deeper, more nuanced view of the universe. It is a journey that stretches from the ancient stargazers who first gazed at the heavens to the spacecraft that now chart the vastness of space, and to the quantum mysteries that lie at the heart of everything. The story of our exploration of the stars is far from over. It is a testament to the enduring curiosity and wonder that drive humanity to seek answers to the greatest questions of existence. Quantum mechanics holds a pivotal role in deciphering some of the universe's most perplexing phenomena, particularly in extreme environments like neutron stars. In these dense, high-energy regions, the behavior of matter is governed by quantum principles that take center stage, allowing astrophysicists to explore exotic states of matter that are otherwise unreachable under normal conditions. In these extreme realms, where the gravitational forces are immense and the environments are far from what we encounter on Earth, the behavior of quantum particles reveals fundamental truths about the universe. Research into these environments has led to remarkable revelations about the interplay between gravity and quantum mechanics, two of the most fundamental forces of nature. This interaction is not just theoretical. It's the key to developing a unified theory of everything, a comprehensive understanding of the universe. By bridging the gap between these two pillars of modern physics, scientists are exploring new frontiers, pushing the boundaries of what we know about space, time, and the very fabric of reality. Furthermore, quantum mechanics isn't only a tool for exploring the cosmos. It also drives innovations in technology that significantly enhance astrophysical research. Technologies like quantum imaging and quantum computing are revolutionizing how we observe and simulate cosmic phenomena. These cutting-edge tools allow scientists to peer deeper into the universe, creating simulations and models that bring previously inaccessible realms into view. The integration of quantum principles into astrophysical studies continues to reveal astonishing insights, blending the microscopic with the cosmic in a seamless dance of discovery. One of the most groundbreaking instruments in this exploration has been the Hubble Space Telescope, launched in 1990. Over the decades, it has reshaped our understanding of the universe in ways previously thought impossible. Its observations of distant supernovae provided the first evidence that not only is the universe expanding, but that the rate of expansion is accelerating. This astonishing discovery led to the formulation of the concept of dark energy, an enigmatic force that seems to permeate space itself, counteracting the gravitational pull that would otherwise slow down the universe's expansion. Hubble has also given us profound insights into the formation and evolution of galaxies. Its stunning images have revealed a breathtaking diversity in galactic structures, ranging from the graceful spirals of galaxies like our own Milky Way to the more peculiar and irregular shapes of distant cosmic formations. By studying the distribution and composition of stars within these galaxies, astronomers have deepened their understanding of how galaxies collide, merge, and grow over time, processes that shape the cosmic landscape on vast scales. Another key contribution of the Hubble Space Telescope has been its role in the study of exoplanets, planets that exist outside our solar system. Hubble's observations have led to the discovery of many such worlds, allowing scientists to study their atmospheres and explore their potential for habitability. This has opened up exciting new questions about life beyond Earth and the possibility that there are other environments in the universe where life could exist. In addition to these revelations, Hubble has captured mesmerizing images of distant nebula, black holes, and other celestial phenomena. These images not only inspire awe, but also offer invaluable insights into the processes that shape the universe. Each discovery, each breathtaking image, adds another layer to our growing understanding of the cosmos, reminding us of the vastness and complexity of the universe while fueling our curiosity for what lies just beyond the horizon of our current knowledge. In the far reaches of our solar system, exploration continues with several ambitious missions designed to expand our understanding of the outer planets and their moons. One such mission is NASA's Europa Clipper, set to launch in 2024. This spacecraft will target Europa, one of Jupiter's icy moons, which is believed to harbor a subsurface ocean beneath its frozen crust. Europa's potential for liquid water and the necessary chemical ingredients for life has made it a prime candidate for the search for extraterrestrial life. The Europa Clipper will conduct detailed reconnaissance of Europa's ice shell and subsurface ocean, searching for signs that this distant world could support life. Another key mission is the European Space Agency's JUICE, Jupiter Icy Moons Explorer, which is scheduled for launch in 2023. While Europa is a primary target, JUICE will also study Jupiter's other major moons, Ganymede and Callisto. Ganymede in particular is fascinating because it is the only moon in the solar system known to possess its own magnetic field. This mission will explore the icy crusts of these moons and investigate the potential existence of subsurface oceans, offering fresh insights into their internal structures and their capacity to support life. Meanwhile, NASA's Dragonfly mission, set to launch in 2027, promises to take a unique approach to studying Titan, Saturn's largest moon. This innovative rotorcraft will fly to multiple locations across Titan, studying its dense atmosphere and surface, which is dotted with rivers and lakes made of liquid methane and ethane. Dragonfly's mission is to explore Titan's prebiotic chemistry and assess whether the moon has the potential to support life. This groundbreaking mission is one of the most ambitious efforts to study an extraterrestrial body, and its findings could reshape our understanding of life in the universe. Through these missions and the ongoing efforts of astrophysicists and space agencies around the world, humanity is making tremendous strides in exploring the cosmos. Each new discovery brings us one step closer to understanding the vast and mysterious universe that surrounds us, offering hope that one day we may unlock the secrets of the stars. There are ongoing discussions and proposals regarding future missions, including the possibility of returning to Uranus and Neptune, the ice giants of our solar system. These missions could involve sending orbiters or landers designed to unlock the secrets of their atmospheres, magnetic fields, and the unique weather phenomena that occur on these distant planets. Each mission brings us one step closer to answering the profound questions about the origins of our solar system and the potential for life beyond Earth. By shedding light on the darker regions of our celestial neighborhood, these missions deepen our understanding of the vast and mysterious cosmos. At the same time, advancements in artificial intelligence are revolutionizing our approach to space exploration. Traditionally, astronomers would manually sift through enormous amounts of data, searching for patterns or anomalies that might lead to groundbreaking discoveries. However, as the universe continues to flood us with vast quantities of information, such as telescope images and various space signals, AI is now stepping in to analyze this data with unprecedented speed and precision. Machine learning algorithms are being trained to recognize subtle patterns in cosmic data that might otherwise escape the attention of the human eye. For instance, AI can spot unusual fluctuations in the light curves of distant stars, which could indicate the presence of exoplanets or even entirely new types of celestial phenomena. This ability not only speeds up the discovery process, but also expands the range of potential discoveries, allowing researchers to identify anomalies that were once beyond our comprehension. Moreover, AI has the extraordinary capability to process data from multiple sources simultaneously. Large-scale projects like the ongoing night sky survey conducted by the Vera C. Rubin Observatory generate vast amounts of data, sometimes reaching petabytes. AI plays a pivotal role by classifying and sorting this data in real time, helping astronomers spot transient events such as supernovae or gravitational waves. These events occur on timescales that are too short for traditional human analysis, but AI can efficiently process these signals, allowing us to understand cosmic phenomena that would otherwise remain hidden. As we continue to seek answers about the universe, the role of AI in enhancing our capabilities is undeniable. This technological evolution not only accelerates the pace of discovery, but also enables us to explore the deepest mysteries of the cosmos. Harnessing the potential of AI moves us one step closer to unraveling the profound enigmas that lie beyond our planet. The construction of new observatories plays a crucial role in our ongoing quest to unravel the mysteries of the universe. As technology progresses, our ability to observe celestial phenomena expands, bringing previously unseen aspects of the cosmos into focus. Each new observatory acts as a powerful eye peering into the vast reaches of space, enabling scientists to collect data about stars, galaxies, and even the elusive dark matter that makes up much of the universe's mass. One of the most significant benefits of constructing new observatories is the advancement of observational technology. These facilities are equipped with state-of-the-art instruments capable of detecting wavelengths of light beyond the reach of older telescopes. While many telescopes focus on visible light, newer observatories explore infrared, ultraviolet, and even radio waves, offering us a more comprehensive view of the universe. This ability to detect different wavelengths reveals the structures and processes of the cosmos that we have yet to fully understand, including the birth of stars, the life cycles of galaxies, and the mysterious energy that drives the expansion of the universe. In addition to enhancing our observational capabilities, many new observatories are being strategically located in areas with optimal conditions for astronomy. These sites are often positioned atop remote mountain peaks or in isolated desert regions, where clear skies and minimal atmospheric interference provide the perfect environment for stargazing. The absence of light pollution at these locations ensures that astronomers can capture sharper, more precise images and gather more accurate data. These ideal conditions allow researchers to unlock deeper insights into the fabric of the universe. Furthermore, each new observatory serves as a center for international collaboration, drawing scientists from all over the world to work together toward a common goal. The exchange of expertise and ideas fosters innovation, leading to breakthroughs that push the boundaries of our scientific knowledge. Through shared observations and discoveries, these global scientific communities unite to confront the unanswered questions of our universe, igniting a sense of wonder and expanding humanity's understanding of our cosmic home. Space tourism, while often seen as a thrilling adventure, holds the potential to significantly enhance our exploration and study of celestial bodies. The advent of commercial space flights opens up space travel to a broader spectrum of people. As more private companies enter the space tourism market, we can expect to see a more diverse range of travelers, each bringing new perspectives and ideas to the field of space exploration. This democratization of space could lead to fresh insights that inspire groundbreaking research and discoveries. Moreover, the growth of the space tourism industry could stimulate significant advancements in technology. The development of spacecraft capable of carrying tourists requires cutting-edge innovations in propulsion, life support systems, and landing mechanisms. These technological advancements, initially designed for commercial purposes, can later be adapted for scientific missions. As the space tourism industry progresses, we are likely to see more efficient and reliable spacecraft, making missions to celestial bodies such as the Moon or Mars more feasible and cost-effective. The synergy between commercial space ventures and scientific exploration creates a powerful feedback loop, driving innovation and pushing the boundaries of what we can achieve in space. Moreover, as space tourism continues to gain traction, it holds the potential to unlock a world of opportunities for scientific exploration. The growing fascination with the concept of visiting space is not just a fleeting trend. It signifies a profound shift in the way we view the cosmos and our place within it. As more people become captivated by the idea of traveling beyond Earth's atmosphere, a ripple effect takes place. The demand for knowledge about our universe surges, prompting governments and private companies alike to direct more resources and funding towards ambitious space missions. The rising interest in space tourism could pave the way for missions to the Moon, Mars, and far beyond. These missions promise to deepen our understanding of distant celestial bodies and explore their potential for human habitation. However, the impact goes beyond just exploration. The rise of space tourism can bring about a new era of collaboration between private enterprises and scientific institutions. These collaborations could lead to unprecedented partnerships where cutting-edge resources, knowledge, and technologies are shared. This holistic approach to space exploration holds the promise of accelerating progress and transforming how we approach the mysteries of the universe. Each launch not only increases the allure of space for millions of people around the globe, but also opens new pathways for deeper scientific discovery. As humanity gazes toward the stars, the dream of interstellar travel captures our collective imagination like never before. With remarkable technological innovations steadily emerging, the dream that once seemed confined to science fiction is becoming more tangible with each passing day. One of the most exciting concepts being explored is the use of light sails, propelled by powerful lasers. By harnessing the immense energy of these lasers, small spacecraft could gradually accelerate, reaching speeds that bring the nearest stars closer within our reach. Over time, such technologies could revolutionize how we travel across the cosmos, turning interstellar exploration from a theoretical idea into a practical pursuit. Another groundbreaking development lies in the realm of nuclear propulsion. Researchers are now investigating nuclear fusion, the same process that powers our sun, as a potential source of energy for spacecraft. In theory, a fusion-powered spacecraft could generate immense thrust, dramatically reducing travel time to distant worlds. Concepts like fusion rockets could be the key to breaking through the current barriers of space travel speed, shrinking what would otherwise be decades-long journeys into mere years. Equally captivating is the prospect of antimatter propulsion. Antimatter, the mirror image of regular matter when it encounters its counterpart, annihilates both, releasing an incredible burst of energy. While the challenges of producing and storing antimatter are immense, the possibilities it holds for space travel are nothing short of revolutionary. If harnessed for propulsion, antimatter could make near-light-speed journeys a reality, fundamentally altering the way we think about the speed and distance of space exploration. At the same time, advanced robotics and artificial intelligence are rapidly becoming indispensable in the future of interstellar missions. These technologies will play a crucial role in navigating the vast, unpredictable expanses of space. They will conduct scientific research, make complex decisions, and carry out tasks that would be unthinkable for human astronauts on distant journeys, potentially light years away from Earth. As we refine these technologies, the dream of reaching other star systems, once confined to the realm of science fiction, may evolve into a tangible reality. The future of telescopes also holds extraordinary potential. These advanced instruments will offer unprecedented views of exoplanets, planets that exist beyond our solar system. Equipped with state-of-the-art technology, future telescopes will enable astronomers to probe the atmospheres of these distant worlds in remarkable detail. By analyzing light filtering through an exoplanet's atmosphere during transits, scientists will be able to determine the composition of the planet's atmosphere, detect chemicals, and even speculate about the possibility of habitability. One of the most significant advancements in this field will be the ability to detect signs of life, or biomarkers, on distant exoplanets. Future telescopes will be able to identify gases such as oxygen, methane, and carbon dioxide, which could point to biological processes. The ability to detect these gases will deepen our understanding of the conditions required for life as we know it, and raise intriguing questions about whether we share the universe with other living organisms. Are we, as far as we know, uniquely alone, or might we find evidence of other forms of life beyond Earth? Another transformative aspect of future telescopes is their ability to directly image exoplanets. Current telescopes often struggle to differentiate these distant planets from the bright glare of their parent stars. However, new techniques such as coronagraphy and interferometry will allow astronomers to capture actual images of these planets. This direct visual evidence will enable researchers to study the surface conditions and atmospheres of exoplanets in much greater detail, leading to a deeper understanding of their diversity and characteristics. As these technologies continue to develop, our perspective on the cosmos may change in ways we can't yet fully comprehend. Each new advancement offers the potential for new discoveries and a greater understanding of the universe. The excitement of discovery is palpable as we look forward to the possibility of uncovering new exoplanets, some of which may bear striking similarities to Earth. These new findings could bring us closer to answering fundamental questions about our place in the universe and whether we are truly alone in the vastness of space. International collaboration in space exploration has proven to be instrumental in pushing the boundaries of human knowledge. By pooling resources, expertise, and talent from nations around the world, scientists and engineers are tackling challenges that individual countries could not overcome alone. These collective efforts result in innovative solutions and have been pivotal in achieving milestones in space exploration. For example, the partnership behind the International Space Station, ISS, is a prime example of how collaboration can lead to significant scientific advancements. By sharing costs, expertise, and technology, these international partnerships make ambitious space missions more feasible. Countries with limited technological resources can benefit from access to advanced technologies and knowledge developed by their partners, accelerating progress and fostering breakthroughs that might not have been possible otherwise. As we continue to explore the universe, the importance of these global collaborations cannot be overstated. They not only make space missions more cost-effective, but also create opportunities for sharing scientific knowledge and technological innovations across borders. Ultimately, these partnerships will continue to be at the heart of humanity's journey into space, propelling us towards a future where the mysteries of the cosmos are no longer out of reach. In the world of scientific research, collaborations between nations and cultures are essential, shaping a dynamic environment where new discoveries thrive. When researchers from diverse backgrounds come together, their unique perspectives on challenges and solutions often lead to breakthroughs that would be impossible through isolated efforts. This rich tapestry of expertise fosters an atmosphere of creativity and innovation, enhancing the scope and depth of research outcomes. One such profound example can be found in the realm of space exploration, where international collaborations have greatly expanded our understanding of distant worlds. The cooperative efforts in the exploration of Mars serve as a prime illustration of this. The findings that have emerged from these joint endeavors have not only shed light on the red planet's surface, but have also introduced the possibility that Mars once hosted liquid water. This discovery holds profound implications for the potential existence of life beyond Earth. As researchers explore further, the question of whether microbial life could have once thrived on Mars becomes a key focus, pushing humanity closer to answering one of its most fundamental questions. Moreover, space exploration does not only serve to advance scientific knowledge, it also plays a critical role in fostering peaceful relations and promoting unity on a global scale. The shared pursuit of understanding the cosmos has the power to transcend national borders, creating a sense of collective human purpose. Initiatives like the Hubble Space Telescope, with its groundbreaking discoveries, have brought scientists together from across the globe. The revelations from this telescope have not only deepened our understanding of the universe, but have also united diverse scientific communities in a common goal: exploring the mysteries of the cosmos. These collaborations are a testament to the fact that when humanity unites in the quest for knowledge, the results can transcend differences and inspire a collective desire to explore, learn, and grow. At the heart of space exploration lies a collective drive to venture beyond the known and discover the unknown. It is not merely about sending spacecraft into the void. It is a profound expression of humanity's innate curiosity and quest for understanding. This drive is especially evident in the study of the moons of Jupiter and Saturn, which present vast potential for scientific exploration. These moons, with their diverse environments, may harbor the conditions necessary for life, making them a central focus of future missions. Europa, one of Jupiter's largest moons, holds particular promise. Beneath its frozen surface lies an ocean of liquid water, a critical ingredient for life as we know it. The possibility that life could exist in such an environment has captivated the scientific community, sparking numerous missions designed to explore the moon's surface and subsurface. Researchers are eager to understand the chemistry and geology of Europa and to search for microbial life in the vast icy depths below. Similarly, Enceladus, a moon of Saturn, has garnered attention due to its impressive geysers that release water vapor and organic molecules into space. These geysers hint at the presence of an underground ocean, and the potential for life in such an environment is a tantalizing possibility. By analyzing samples from these geysers, scientists hope to unlock new insights into the moon's habitability and its geological processes, which could reveal much about the broader conditions that govern life in the solar system. The discovery of life, or even the building blocks of life on any of these moons, would be a groundbreaking moment in human history. It would not only change our understanding of life's resilience, but also redefine our place in the universe. Beyond Europa and Enceladus, the other moons of Jupiter and Saturn present a remarkable array of environments, each offering its own potential for discovery. From Ganymede, the largest moon in the solar system, with its magnetic fields and thick atmosphere, to Titan, Saturn's largest moon, with its lakes of liquid methane, these moons provide a rich canvas for scientific exploration. Each one holds secrets about planetary formation, atmospheric conditions, and the potential for life that could change our understanding of the cosmos. By studying these moons, scientists are not only unraveling the mysteries of these celestial bodies, but are also taking crucial steps toward understanding broader questions about habitability and the mechanisms that govern the universe. The search for life on these distant moons is not just about the moons themselves. It is about gaining insights into the conditions that might support life elsewhere in the galaxy. As humanity continues to push the boundaries of space exploration, one of the most exciting areas of research involves the concept of time travel. Though still firmly within the realm of theoretical physics, the idea of time travel raises intriguing possibilities for the study of cosmic anomalies. Imagine being able to travel back in time to witness the birth of stars or the formation of the universe itself. Such an ability would allow scientists to observe firsthand the events that shaped the cosmos and gain valuable insights into phenomena like black holes, supernova remnants, and the nature of dark matter. The theoretical study of time travel opens up an entire field of speculation, one where researchers could examine cosmic events in ways previously unimaginable. The ability to witness these events in their natural progression would provide data that could refine existing models and help scientists better understand the forces at work in the universe. Time travel could also provide a new perspective on the origins of cosmic anomalies, such as primordial black holes or the formation of the first stars. By tracing the evolution of these phenomena over time, scientists could form a clearer picture of the universe's overall evolution. However, despite its fascinating possibilities, time travel remains a concept riddled with paradoxes and challenges. The complexities it introduces to our understanding of physics, space, and time are still beyond our full comprehension. Yet, the very act of contemplating time travel encourages us to think in new ways about the universe. It forces us to consider how the mysteries of time and space might be intertwined in ways we have yet to fully grasp, pushing the boundaries of scientific thought. As humanity stands on the threshold of exploring other planets, particularly Mars, new ethical questions arise, particularly around the idea of colonization. One of the most pressing concerns is the potential disruption of alien ecosystems. The possibility of harming microbial life or unique environments on other worlds mirrors the ecological impacts that early human explorers had on indigenous populations and ecosystems on Earth. This raises an important ethical dilemma. How should we approach the colonization of planets while ensuring that we do not destroy or harm any potential forms of life, no matter how simple or primitive they may seem? Another significant ethical consideration is the question of ownership. Who has the right to claim and inhabit other worlds? The Outer Space Treaty of 1967 provides some guidance, asserting that space exploration should benefit all of humanity and that no nation or group can claim sovereignty over celestial bodies. However, as private companies begin to play an increasingly large role in space exploration, the lines between public interest and private ownership of space resources may become blurred. This has the potential to lead to conflicts over the rights to exploit these resources, reminiscent of the colonial practices that have shaped Earth's history. These complex ethical issues require careful consideration as humanity ventures further into the cosmos. The future of space exploration will not only be defined by the technologies we develop, but also by the values we choose to uphold as we reach for the stars. The challenge of human settlement on another planet is a profound undertaking, and the questions it raises are as complex as they are crucial. Colonizing a new world forces us to confront fundamental concerns about governance, social structures, and the welfare of those who would call this new world home. How do we ensure that this new society, far from Earth, reflects the values of respect, equity, and ethical treatment? What frameworks can we put in place to protect against the exploitation of resources, the degradation of the environment, or even inequality among settlers themselves? These are not merely hypothetical questions, but practical dilemmas that will define our future. We must look to history for guidance. Humanity's past offers us both warnings and lessons on how not to approach new frontiers. Our new exploration must be grounded in a philosophy of respect and stewardship, one that promotes fairness and seeks to preserve the delicate balance of life. The choices we make today, as we consider venturing into the vast unknown of space, will shape not only our interplanetary ambitions, but will also lay the ethical foundation for generations to come. Our approach to space colonization should not merely be about expanding our physical reach, but also about advancing our moral compass in a way that honors life in all its forms. At the heart of these discussions is the concept of habitability, an area of intense scientific inquiry. Researchers define habitable zones as regions around stars where conditions are just right for life to exist, as we understand it. These zones, often called the Goldilocks zones, are reminiscent of the fairy tale where everything is just right, not too hot and not too cold. The critical factor is the distance from the star, which allows for liquid water to exist on a planet's surface, a vital ingredient for life. If a planet is too close to its star, the water boils away, too far, and it freezes. However, the habitability of a planet is not determined solely by its location within this zone. Other factors, such as the star's size and temperature, come into play. For example, a smaller, cooler star like a red dwarf will have a habitable zone closer to it, while a larger, hotter star like our Sun will have a much broader habitable zone. What's more, scientists have expanded the search for life beyond traditional planets, considering moons orbiting gas giants, exoplanets, which might also lie within these life-friendly regions. Yet the idea of habitability is not a guarantee. Not all planets within these zones are suitable for life. The conditions on these planets can be far more hostile than we anticipate. Extreme weather, lack of a protective atmosphere, and intense radiation from a star can make survival impossible. Venus, for instance, is in our Sun's habitable zone, yet its thick, toxic atmosphere and runaway greenhouse effect make its surface an inhospitable wasteland. In stark contrast, Earth, with its abundant life and balanced ecosystems, showcases the delicate interplay of factors required for a planet to sustain life. As technology advances, astronomers are refining their understanding of what constitutes a habitable planet. They are factoring in a planet's atmospheric composition, climate stability, and even its magnetic field, all of which play crucial roles in determining whether a world can support life. With these new insights, we are expanding our search for life beyond Earth, looking for those elusive planets or moons that might harbor the building blocks of life, or perhaps life itself. The search for extraterrestrial life has captured the human imagination for centuries. Many believe that, given the sheer scale of the universe, it seems statistically improbable that Earth is the only cradle of life. There are billions of galaxies, each with billions of stars, and many of these stars have planets located in their habitable zones. The numbers alone suggest that life in some form might be common in the universe. Moreover, recent discoveries within our own solar system have only fueled this belief. The subsurface oceans of Jupiter's moon Europa and the salty lakes on Mars suggest the possibility of microbial life existing in environments we once considered too hostile. In addition, extremophiles, organisms that thrive in Earth's harshest environments, demonstrate that life can exist in conditions once thought uninhabitable. These resilient life forms, which survive in boiling hot springs, frigid ice, or even deep ocean vents, suggest that life is more adaptable and versatile than previously imagined. If life on Earth can endure in such extreme conditions, why couldn't similar life forms exist on distant planets or moons? However, this optimism is not shared by all. Some argue that the absence of evidence for extraterrestrial life presents a serious challenge to the idea that life is abundant in the universe. Despite decades of searching through programs like the Search for Extraterrestrial Intelligence, we have yet to receive definitive signals or encounter any form of communication from intelligent civilizations. This paradox, the absence of detectable evidence despite the high probability of life, raises doubts about the prevalence of advanced civilizations. Furthermore, the uniqueness of Earth's conditions adds another layer of skepticism. Our planet's stable climate, its position within the habitable zone, and the presence of liquid water are exceptional. And some argue that these factors may be so rare that intelligent life capable of technology and communication could be exceedingly scarce. This perspective suggests that while microbial life may be common, complex life forms with the ability to develop technology and engage in interstellar communication might be far less frequent, if not fleeting. This line of thinking leads to a somber possibility that we may be alone in our technological development, or that advanced civilizations may only emerge for brief periods in the lifespan of the universe. Perhaps life elsewhere in the universe exists in forms we cannot yet fathom, microbial life in the hidden depths of moons and planets, but not the complex civilizations we envision. Despite the ongoing debate, the search for extraterrestrial life continues to captivate both scientists and the public alike. And in the process, it forces us to confront the most profound questions about our own existence. What makes a planet truly habitable? What does the future of space exploration look like? And, perhaps most intriguing of all, are we truly alone in the universe? Through the study of extremophiles and the exploration of habitable zones, we are expanding our understanding of life's resilience and its potential to thrive in the unlikeliest of places. As we peer deeper into the cosmos, we are faced not only with the search for other life forms, but with the larger question of what it means to be human in an increasingly interconnected universe. The astonishing resilience of extremophiles, organisms that thrive under extreme conditions, forces us to reconsider long-held assumptions about the limits of life. These hardy creatures endure environments that defy our expectations of what life can withstand: radiation, extreme pressure, and temperature variations that seem utterly inhospitable to most forms of life. By investigating how extremophiles manage to survive these harsh conditions, scientists gain crucial insights into the fundamental nature of life itself. More importantly, they can apply this understanding to the search for life elsewhere in the universe. Recent research has even identified specific genes responsible for radiation resistance in extremophiles. These discoveries not only expand our knowledge of life on Earth, but also serve as a guide for future space exploration. If life can persist in such extreme environments here, could it also survive on other planets or moons? With each new breakthrough, extremophiles challenge the very definition of what constitutes a habitable environment, opening up possibilities for life in places once thought too harsh to support it. As we look deeper into the vastness of space, these remarkable organisms remind us of the boundless adaptability of life. Their existence in such extreme conditions brings into question the very nature of life's potential across the universe. Indeed, our search for life beyond Earth has been given new impetus by these tiny, resilient beings that demonstrate how life could survive in the most unlikely of places. Whether on distant exoplanets or moons within our own solar system, extremophiles show us that life's limits are far from where we once thought they were. Alongside these advancements, the discovery of water vapor in the atmospheres of exoplanets has ignited fresh excitement in the scientific community. Water, as we know, is essential for life. Its presence on distant worlds has raised the possibility that conditions for life might exist far beyond our own solar system. As technology advances, particularly with the help of space telescopes like the James Webb Space Telescope, astronomers have begun to gather vital data about the atmospheres of planets orbiting distant stars. For example, Webb has provided unprecedented insight into the chemical composition of exoplanetary atmospheres, unveiling a complex mix of gases that could support life. Among the most exciting discoveries is the detection of water vapor, a critical element for life as we understand it. Along with this, scientists have detected the presence of carbon dioxide and methane, gases that can be produced by biological processes. These gases, when found in specific ratios, could suggest the presence of microbial life functioning much like it does on Earth. Furthermore, some studies have indicated that certain exoplanets could possess atmospheres capable of sustaining temperatures that are conducive to life. These planets, located within the habitable zone of their stars, are in the Goldilocks zone, where conditions are just right for liquid water to exist. The diversity of chemicals detected in these atmospheres, including organic compounds, raises intriguing questions about the types of life that could evolve under these vastly different conditions. As scientists continue to probe the atmospheres of distant exoplanets, they edge closer to answering one of humanity's oldest and most profound questions. Are we alone in the universe? Each discovery fuels not only our curiosity, but also our imagination. We now realize that life could manifest in a myriad of forms on planets orbiting stars far from our own. This ongoing exploration deepens our understanding of the cosmos and forces us to redefine what it means for a planet to be habitable. Equally revealing are the isotopic signatures found in meteorites, ancient relics from the early solar system. These meteorites carry with them clues to the origins of life itself. Isotopes, atoms that differ in the number of neutrons they contain, can tell us about the environments in which these meteorites were formed and the chemical processes that shaped them. By studying the isotopic ratios in meteorites, researchers are able to detect the building blocks of life, including certain amino acids and other organic compounds essential for life. Some of the most fascinating isotopic signatures suggest that these organic materials might not have originated on Earth at all. Could meteorites have delivered life's building blocks from other parts of the universe? This idea raises the possibility that Earth's life forms may have had extraterrestrial origins, perhaps brought here by meteorite impacts during the early stages of our planet's history. By analyzing these isotopic signatures, scientists are not only piecing together the history of life on Earth, but also gaining valuable insights into the potential for life elsewhere in the cosmos. These meteorites are invaluable time capsules, preserving a record of the chemical processes that unfolded billions of years ago. Their study offers us a glimpse into the cosmic history of our universe and provides clues about the conditions under which life might have emerged on other planets. Through this research, scientists are unraveling the mystery of where we come from and perhaps where we might find life beyond our own planet. However, as we continue to search for life, one question remains unanswered. If the universe is so vast, capable of supporting countless habitable planets, why haven't we detected signs of intelligent extraterrestrial civilizations? This conundrum, known as the Fermi paradox, has puzzled scientists and thinkers for decades. Given the billions of stars and potentially habitable planets scattered across the galaxy, it seems inevitable that intelligent life should exist elsewhere. Yet, the silence is deafening. Several theories have emerged to explain this paradox. One of the most compelling is the rare Earth hypothesis, which suggests that the specific conditions necessary for complex life to thrive are extremely rare. While simple life forms, like bacteria, might be common throughout the universe, the combination of factors that make Earth so uniquely suited for complex life, such as a stable star, the right planetary conditions, and a protective magnetic field, could be incredibly rare. According to this theory, intelligent life may be an anomaly, one that is far less common than we might have hoped. Another theory, known as the Great Filter Hypothesis, suggests that intelligent civilizations might tend to self-destruct before they can develop advanced technology capable of interstellar communication. Whether through nuclear war, climate change, or pandemics, civilizations might reach a point in their development where they can no longer overcome the challenges they face. If most intelligent civilizations do not survive long enough to develop the technologies necessary for space exploration or communication, this could explain why we haven't detected any extraterrestrial signals. These theories offer potential explanations for the silence we observe, but the question remains, are we truly alone, or is the universe teeming with intelligent life waiting to be discovered? As our technological capabilities continue to improve, we may one day find the answer to this age-old mystery. Until then, the search for life in all its forms continues to inspire awe and wonder, pushing the boundaries of our understanding and expanding the horizons of what is possible. Some scientists propose an intriguing idea that highly advanced civilizations may intentionally choose to remain undetected by us. This hypothesis is closely tied to the so-called zoo hypothesis, which suggests that extraterrestrial civilizations deliberately avoid contact with humanity, much like zookeepers strive not to disturb the animals in their care. These advanced beings may observe us from a distance, possibly following a strict code of ethics that forbids interference in our natural development. Their reasons for remaining hidden are speculative, but they point to a profound truth about the vast and mysterious nature of the universe. As we search the stars for signs of intelligent life, we are left to wonder, are we truly alone, or are we merely a part of a silent cosmic tapestry? In this context, the Drake equation emerges as an essential tool in the quest to understand the likelihood of intelligent life beyond Earth. Developed by the American astronomer Frank Drake in 1961, the equation seeks to estimate the number of advanced civilizations in our galaxy with whom we might be able to communicate. At its core, the equation incorporates a series of probabilities that represent the various conditions necessary for intelligent life to emerge. These include the rate at which stars form, the fraction of stars that have planets, and the likelihood that life develops on those planets. By multiplying these factors, the equation attempts to calculate how many technological civilizations might exist in the Milky Way. What makes the Drake equation so compelling is not just its ability to generate a potential numerical answer, but its role in framing the scientific conversation around the search for extraterrestrial intelligence. Rather than offering a single definitive answer, the equation breaks down the complex conditions that allow for life into smaller, more digestible components. Each factor provides insight into what we know, and equally important, what we don't know, pushing the boundaries of research in fields as diverse as astronomy, biology, and physics. As our understanding of each factor improves, our estimates of the probability of intelligent life elsewhere grow more refined. The equation has sparked a wide range of scientific endeavors, including the search for extraterrestrial intelligence, SETI. Using radio telescopes and other observational tools, SETI scientists listen intently for signals that might indicate the presence of intelligent beings hidden in the vast expanse of the universe. Every signal received, or the lack thereof, contributes to our understanding of the variables within the Drake equation, continuously refining our calculations and expanding our curiosity. These efforts represent more than just a technical pursuit. They are an invitation to contemplate our place in the cosmos. As we consider the possibilities of extraterrestrial life, the Drake equation reminds us of the fragility and uniqueness of our own civilization. By contemplating the odds of other intelligent beings, we are forced to reflect on what it means to be human. The search for life, whether we find it or not, serves as a catalyst for deepening our understanding of the universe and our role within it. Over the years, scientists have come across a number of perplexing signals that some have speculated might be evidence of extraterrestrial intelligence. Perhaps the most famous of these is the WOW signal, detected in 1977 by astronomer Jerry R. Ehman while working on the SETI project at the Big Ear Radio Telescope in Ohio. The WOW signal was a brief but powerful burst of radio waves, lasting a mere 72 seconds, and it appeared to come from the direction of the constellation Sagittarius. Despite extensive efforts, the source of the signal has never been identified. Its extraordinary strength and the narrow bandwidth of the signal led many to wonder, could this be a communication from an alien civilization? Fast radio bursts, FRBs, represent another mysterious phenomenon that has captured the imagination of scientists. These intense bursts of radio waves last only milliseconds, but they can release as much energy as our sun does in an entire day. Some of these bursts are observed to repeat in cycles, leading researchers to speculate that they might have an artificial origin. While many of these FRBs have been traced back to natural astrophysical sources like magnetars and neutron stars, the possibility that some could be engineered signals continues to fuel debates within the scientific community. Further adding to the intrigue, the so-called LGM-1 signals discovered in the 1960s also raised excitement. The term "little green men" was coined by researchers jokingly to describe these signals, which were initially thought to be potential communications from extraterrestrial life. However, these signals were later identified as coming from rapidly rotating neutron stars, known as pulsars, which emit beams of radiation as they spin. Still, the mystery of unexplained signals remains, and many scientists continue to question whether some signals may conceal their true origins, keeping us guessing about what they might represent. In 2017, researchers detected yet another perplexing phenomenon, an optical signal from a distant star known as KIAC 846282, or Tabby star. This star exhibited irregular dimming patterns that couldn't be easily explained by natural processes. One theory suggested that the dimming might be caused by massive artificial structures, possibly a Dyson sphere or other megastructures constructed by an advanced civilization. While subsequent studies have suggested more natural explanations, the possibility of an extraterrestrial origin continues to captivate the scientific imagination. This event is just one example of how unexplained phenomena continue to shape our understanding of the universe, offering tantalizing clues about the mysteries that lie beyond our planet. As these anomalies continue to be explored, they remind us of the vastness and complexity of the cosmos. The ongoing search for signs of extraterrestrial intelligence serves as both a scientific pursuit and a profound existential question. What do these signals, or the absence of them, tell us about the universe we inhabit? Equally fascinating is the study of interstellar microbes, tiny organisms that have been discovered in the vacuum of space. These microbes challenge our understanding of life's resilience and its potential to exist beyond Earth. If such life can survive the harsh conditions of space, extreme cold, radiation, and the vacuum of space, then it suggests that life may be more common in the universe than we once imagined. This idea raises the possibility that life could exist on planets far beyond our solar system, waiting to be discovered. One of the most compelling theories emerging from this research is panspermia, the idea that life could be spread across the cosmos through cosmic materials such as meteorites or comets. If microorganisms can survive the journey through space, they might be carried from one planet to another, potentially seeding life on worlds far from Earth. This idea forces scientists to reconsider the origins of life on Earth. Rather than being a rare, unique event, the emergence of life could be part of a larger cosmic process, one that unfolds across the universe in ways we have yet to fully understand. The discovery of life beyond Earth, whether through interstellar microbes or advanced civilizations, has the power to redefine our place in the cosmos and forever change the way we view our own existence. Microbes, those microscopic life forms that inhabit even the harshest environments on Earth, provide a fascinating glimpse into the broader possibilities for life beyond our planet. Studying how these organisms survive in extreme conditions, such as boiling hot springs, frozen ice caps, and acidic waters, offers a profound insight into the essential conditions necessary for life to thrive. When we delve into the genetic adaptations and metabolic processes of these resilient microbes, we not only understand the limits of life, but also uncover clues about the types of environments where life could develop elsewhere. This growing body of research holds immense potential for guiding future missions to planets and moons in our solar system and beyond. By targeting locations where extremophiles, organisms that thrive in extreme conditions, are likely to be found, astrobiologists can direct their efforts toward areas that hold the greatest promise for discovering alien life. In essence, these interstellar microbes challenge our conventional understanding of life's origins. They hint at the possibility that life is not a rare, improbable occurrence, but rather something that could be widespread across the cosmos. As we continue to explore and unravel the mysteries surrounding these resilient microorganisms, we deepen our understanding of how life might have first emerged, not just on Earth, but potentially across the entire universe. One of the most intriguing places to search for extraterrestrial life is Europa, one of Jupiter's moons. Europa stands out due to its unique and compelling features, making it a prime candidate in the quest to uncover signs of life beyond Earth. Beneath its thick icy surface lies a global ocean, which may contain more water than all of Earth's oceans combined. Liquid water, as we know it, is a fundamental prerequisite for life, and the discovery of such a vast ocean underneath Europa's frozen shell presents an exciting possibility for astrobiologists. But the potential for life on Europa does not end there. Scientists believe that this vast ocean may be in direct contact with the moon's rocky mantle, creating the possibility of chemical interactions similar to those that occur on Earth's hydrothermal vents, deep sea environments where life flourishes in the absence of sunlight. These vents are known to host a range of microorganisms that thrive in extreme conditions, driven by the chemical energy from the Earth's interior. On Europa, the interaction between the ocean and rocky mantle could create an environment rich in organic compounds, essential building blocks for life. Europa's relatively young surface is another intriguing aspect of this moon. It is marked by long fractures and ridges, which suggests significant geological activity. This constant renewal of the icy surface could facilitate the transfer of nutrients and energy from the subsurface ocean to the surface, further enhancing the chances of life taking hold. A thin atmosphere, primarily composed of oxygen, also hints at processes that could allow for an exchange of energy between the surface and the ocean below. With upcoming missions, such as the European Space Agency's Jupiter Icy Moons Explorer and NASA's Europa Clipper, set to launch in the next few years, scientists are poised to gather more evidence. Each new discovery has the potential to bring us closer to understanding whether Europa could be a cradle for extraterrestrial life. The Milky Way, our cosmic home, is a galaxy of incredible complexity and beauty, with its structure and composition continuing to captivate astronomers. At its heart lies a dense bulge composed mainly of older stars, surrounding a supermassive black hole known as Sagittarius A star. This central region plays a crucial role in the dynamics of the entire galaxy. Surrounding this bulge is a flat, rotating disk where most of the galaxy's gas, dust, and young stars are located. This disk is the beating heart of the Milky Way, hosting vibrant, star-forming regions and swirling clouds of interstellar material. Beyond the disk extend the spiral arms of the galaxy, which form a stunning and recognizable pattern visible even from Earth. These arms are dynamic features, not static, and they are filled with young, hot stars. It is in these arms that regions of intense star formation occur, and where clusters of stars and nebulae, vast clouds of gas and dust, showcase the diverse and beautiful life cycle of stars. The stars within these arms are primarily young and bright, and they serve as prominent light sources in the galaxy. Beyond the visible disk of the Milky Way lies the enigmatic halo, a sparse and largely empty region that encircles the galaxy. Composed of ancient stars and globular clusters, dense collections of stars, the halo is home to some of the oldest objects in the universe. Additionally, it is thought to contain a significant amount of dark matter, a mysterious substance that cannot be seen directly, but whose gravitational effects are crucial in shaping the galaxy's overall structure. Dark matter is believed to make up a large portion of the Milky Way's total mass, influencing the motion of stars and affecting the galaxy's overall dynamics. The Milky Way's chemical composition is just as fascinating as its structure. It is made up of a complex mix of elements that have been forged in the hearts of stars over billions of years. Heavier elements like carbon and oxygen enriched through stellar evolution are scattered across the galaxy whenever stars explode as supernovae. These cataclysmic events contribute to the ongoing cycle of star formation, enriching the cosmic chemistry of the galaxy and influencing the birth of new stars and the formation of planets, some of which may have the conditions necessary to support life. The Milky Way is far more than a mere collection of stars. It is a dynamic, ever-evolving ecosystem filled with a multitude of astronomical phenomena. One of the most intriguing and complex aspects of this ecosystem is the globular clusters that orbit the galaxy. These spherical collections of stars, often containing thousands to millions of stars, provide fascinating insights into the early stages of galactic formation. What sets globular clusters apart is their immense age and density. Many are believed to have formed around 12 to 13 billion years ago, making them some of the oldest objects in the universe. The age and density of globular clusters challenge traditional theories of galactic formation. According to earlier models, galaxies are thought to have developed through a gradual process of accumulation and merging of smaller structures. In this context, we would expect to find younger clusters that reflect the ongoing development of galaxies. However, the existence of these ancient globular clusters suggests that galaxies may have formed much more quickly than previously thought, leading astronomers to reconsider our understanding of how galaxies, and the stars within them, came into existence. However, the presence of ancient globular clusters raises profound questions about their origins. These celestial objects appear to have formed well before the galaxies they currently inhabit, suggesting they may have followed a separate evolutionary path. Rather than emerging from star formation within their host galaxies, these clusters show characteristics that imply they may have formed independently in the early universe. Eventually, they were captured by the gravitational pull of larger galaxies. This scenario challenges existing models of cosmic evolution, prompting astronomers to rethink their understanding of galaxy and star formation. Globular clusters are unique in their dense packing of stars, which are mostly old and metal-poor. In astronomical terms, metal refers to elements heavier than hydrogen and helium, which are forged in the interiors of stars. If these clusters had formed in the same environments as other stellar populations, we would expect a broad range of metallicities. Instead, the uniformity of the metal content among globular clusters suggests that their stars originated in a different setting, likely in the early universe before many stars had exploded and recycled metals into their surroundings. This stark difference in formation conditions compels astronomers to look beyond simpler models and consider more complex, dynamic histories for these clusters and their host galaxies. The study of globular clusters opens a window into the universe's early days, where initial conditions could have led to vastly different development paths. These ancient structures serve as relics from a time long before the galaxies they now occupy, providing a unique glimpse into the forces that shaped the cosmos. As scientists continue to unravel the mysteries of globular clusters, they uncover more about the evolution of our galaxy and the conditions that gave rise to its stellar populations. The more we understand these clusters, the more we learn about the processes that shaped not only our galaxy, but the universe itself. Variable stars offer another fascinating area of study in the realm of astronomy. These stars are defined by their fluctuations in brightness, which can occur for a variety of reasons, from intrinsic stellar processes to extrinsic influences such as interactions with nearby objects. Some variable stars, like Cepheid variables, pulse rhythmically, expanding and contracting in a predictable manner. These pulsations are not just an interesting quirk, they are crucial for astronomers. By studying the period and amplitude of a Cepheid's pulsations, astronomers can determine its distance from Earth with remarkable precision. This ability makes these stars indispensable in the cosmic distance ladder, helping to map out the vast scale of the universe. On the other hand, eruptive variable stars such as novae and supernovae provide a glimpse into the explosive ends of stellar life cycles. These dramatic outbursts reveal the underlying processes of stellar evolution, and particularly in the final stages of a star's existence. The study of these explosive events can help answer critical questions about the nature of stellar death and the materials released into the cosmos during such cataclysmic events. What makes variable stars even more intriguing is their unpredictability. Some exhibit erratic, sudden changes in brightness that cannot be easily explained. These irregularities challenge our current understanding and suggest that there is much more to learn. Factors such as magnetic fields or the influence of companion stars can play a role in these dramatic fluctuations. Each new discovery regarding variable stars presents a unique puzzle for astronomers, urging them to refine their models and explore new hypotheses about the forces at play in the universe. Moreover, the study of variable stars contributes significantly to our understanding of the structure and history of the Milky Way. By mapping their locations and monitoring their brightness, astronomers can identify distinct stellar populations and measure the distribution of mass across the galaxy. These insights help scientists paint a more detailed picture of the Milky Way's evolution, contributing to a broader understanding of how galaxies, including our own, have developed over billions of years. The motion of stars within our galaxy tells an even deeper story about the nature of unseen, massive objects that may lie hidden in the depths of space. Certain stars exhibit unusual orbital patterns that suggest the presence of mysterious entities, such as black holes or dark matter. For example, in the center of the Milky Way, there resides a supermassive black hole known as Sagittarius A*. By observing the orbits of stars near this invisible object, astronomers have determined its mass to be millions of times that of the Sun. Despite being invisible to traditional instruments, its immense gravitational pull is evidenced by the rapid motion of nearby stars. This discovery underscores the power of invisible forces in shaping the structure of the galaxy. Beyond individual stars, the collective motion of stars across the Milky Way reveals the presence of dark matter. This elusive substance does not emit light or radiation, yet its gravitational influence is felt across vast cosmic distances. Stars located in the outer regions of the galaxy exhibit motion patterns that suggest there is far more mass influencing their orbits than can be accounted for by visible matter alone. This observation has led astronomers to conclude that a large portion of the mass in the universe is made up of dark matter, which, although invisible, plays a crucial role in shaping the movements of stars and galaxies. The study of star orbits and the gravitational effects of dark matter is central to our understanding of both the Milky Way and the broader universe. These investigations offer critical clues about the structure of galaxies and the unseen forces that govern their behavior. By piecing together the motion of stars, scientists can begin to infer the existence of massive objects that are invisible to the naked eye. This exploration challenges our perceptions of the cosmos, urging us to reconsider what we know about the universe's composition and the forces that shape it. The discovery of a cosmic void within our galaxy provides yet another profound shift in our understanding of the universe. A cosmic void is a vast region of space with a remarkably low density of galaxies. When such voids are identified within the Milky Way, they challenge our ideas about the structure of the universe. These empty expanses of space serve as natural laboratories, offering insights into the forces at work on the largest scales. By studying these voids, scientists can better understand the formation and evolution of galaxies over billions of years. One of the most significant implications of discovering a cosmic void is the potential impact it has on our understanding of dark matter. Generally, cosmic voids are known to have a lower concentration of dark matter, which is a crucial component of the gravitational framework that holds galaxies together. By exploring these empty regions, astronomers can gather valuable information about how dark matter interacts and how it contributes to the overall structure of the universe. This research could lead to refinements in existing theories about galaxy formation and the role of dark matter in shaping the cosmic web. As astronomers continue to explore these vast, empty regions, they uncover more about the intricate structure of the universe. Each discovery of a cosmic void adds a new layer to our understanding of how galaxies evolve and how the universe itself has been shaped over billions of years. Through the study of these voids, scientists are piecing together a more comprehensive picture of the cosmos, revealing the forces and processes that govern its grand design. Uncovering a void within our galaxy could significantly reshape our understanding of cosmic evolution. It may reveal that our galaxy, like many others, has undergone complex processes over time, which led to the creation of these immense voids. Such discoveries challenge existing theories about the uniformity and isotropy of the universe, concepts suggesting that the universe should be roughly the same in every direction. The existence of these voids, where matter is sparse, defies this assumption and presents us with regions that diverge sharply from the average density of the cosmos. These revelations provide a new lens through which to examine the behaviors of galaxy formations and help explain why certain regions of space are densely populated with galaxies, while others remain eerily empty. This new insight is more than a simple observation. It has broader implications for our understanding of the universe's life cycle. The study of cosmic voids contributes directly to piecing together the narrative of the cosmos. It aids astronomers in developing strategies to interpret the large-scale structure of the universe as a cohesive whole. This understanding could lead to a clearer picture of the fundamental principles governing the universe's expansion, offering critical clues about the forces driving its evolution. Each void, as it turns out, tells a compelling story not just about our galaxy, but about the larger universe and humanity's place within it. Meanwhile, cosmic rays, those high-energy particles that constantly bombard the Earth from deep space, offer another intriguing avenue of research. Primarily composed of protons, these cosmic rays may also include heavier atomic nuclei and electrons. When these particles enter Earth's atmosphere, they trigger a cascade of secondary particles, a phenomenon known as a cosmic ray shower. The study of these showers offers profound insights into the nature of cosmic rays themselves, and more importantly, the events and processes taking place across our galaxy. Cosmic ray showers act as messengers from distant corners of the universe. As they travel across vast stretches of space, these particles carry signatures of their origin, providing astronomers with valuable data about the cosmic events that produce them. Their energy levels, for instance, can hint at monumental events like supernova explosions or interactions with black holes. By analyzing the characteristics of these cosmic showers, scientists can glean important information about the environments that birthed them and how they contribute to the galaxy's overall energy balance. Beyond their role in revealing the nature of distant cosmic events, cosmic ray showers are also crucial for identifying anomalies in our own galaxy. An unexpected surge in high-energy cosmic rays from a particular region might point to unusual phenomena occurring in that area, such as the presence of a pulsar or other dense astrophysical objects. These anomalies push the boundaries of our current understanding of the cosmos, urging scientists to refine existing models of galactic processes and explore new theories about the universe's workings. In addition, the study of cosmic rays provides insight into the interstellar medium, the matter and radiation that fill the space between star systems. Variations in cosmic ray behavior can signal changes in the density and composition of this medium, which plays a pivotal role in the formation of new stars and the overall structure of our galaxy. Cosmic ray showers, in this sense, act as a window into the dynamic, sometimes chaotic, nature of our galactic environment, offering glimpses of a universe that is constantly evolving and surprising. Equally captivating are the Magellanic Clouds, two irregular dwarf galaxies that lie just a few million light-years away from Earth. These galaxies, known as the Large Magellanic Cloud, LMC, and the Small Magellanic Cloud, SMC, are among the closest galactic neighbors to the Milky Way. Their proximity allows astronomers to observe them with remarkable detail, revealing unique properties that enrich our understanding of the Milky Way and its neighbors. One of the most fascinating aspects of the Magellanic Clouds is their role in the formation of new stars. Both galaxies are teeming with young, vibrant stars and stellar nurseries where new stars are being born. These regions are also active with intense stellar phenomena, including supernova explosions. Studying these events provides astronomers with valuable insights into the life cycle of stars, the processes of star formation, and the broader dynamics of stellar evolution. This, in turn, offers critical information about the history of our own galaxy and the broader cosmic processes that shaped it. The Magellanic Clouds are not passive objects in the sky. They are actively engaged in a gravitational interaction with the Milky Way. Over time, these galaxies have been observed to lose gas and stars to the Milky Way, creating spectacular tidal tails of stars and gas that trail behind them. This interaction serves as a natural laboratory for studying galaxy evolution and provides a window into the forces that govern the formation and movement of galaxies. Furthermore, the Magellanic Clouds offer a unique opportunity to study dark matter. The distribution of stars and gas within these galaxies suggests the presence of an unseen substance that affects their motion and structure. By studying the dynamics of these galaxies, astronomers can learn more about the role dark matter plays in the formation and evolution of galaxies. In this sense, the Magellanic Clouds are not just interesting celestial objects. They are essential keys to unlocking the mysteries of our universe. Mapping the Milky Way is no small feat. This task is complicated by the fact that we are trying to chart a galaxy from within it. Imagine attempting to draw a map of a vast, foggy city while being stuck inside, unable to see the full picture. The Milky Way spans about 100,000 light-years across and contains billions of stars, making it incredibly difficult to map out in its entirety. Our location within the galaxy obscures our view, and dense cosmic dust can further hinder our line of sight, making it challenging to gather data on distant stars. The sheer scale and dynamics of the Milky Way complicate the task even further. Different regions of the galaxy rotate at different speeds, which means that the positions of stars and star clusters may not be where we think they are when we account for their movement over time. Understanding these complexities requires sophisticated tools and techniques, such as telescopes and satellite measurements, to peer through the cosmic dust and provide a clearer picture of the Milky Way's structure. Despite these obstacles, the effort to map our galaxy is ongoing and is slowly but surely revealing the intricacies of our cosmic home. The vast complexities of our universe present continuous challenges in mapping and understanding the structure of the Milky Way galaxy. Gravitational influences from massive cosmic objects such as black holes and star clusters often distort the measurements we rely on, leading to miscalculations in the distances and positions of objects within our galaxy. These gravitational forces, while predictable to some extent, can still lead to anomalies that are difficult to interpret, such as unexpected star formations and the mysterious presence of dark matter. Dark matter, which constitutes a significant portion of the Milky Way's mass, remains invisible to the naked eye, compelling scientists to infer its existence through its gravitational effects on visible matter. These forces can create peculiar and irregular patterns in the distribution of stars, which raises important questions about the true structure of the galaxy itself. Understanding how dark matter interacts with normal, visible matter is essential for refining our galactic maps and improving our cosmic models. Despite these obstacles and mysteries, scientists relentlessly push forward, continuing their quest to unlock the secrets of the Milky Way. With the help of cutting-edge technology, including space observatories and increasingly sophisticated computational models, astronomers are making remarkable strides in uncovering new insights about our cosmic home. Each anomaly encountered provides a piece of the puzzle, gradually painting a richer, more nuanced picture of the universe. This journey invites us to look deeper into the night sky, knowing that each discovery leads to more questions and greater curiosity. One of the most fascinating discoveries that has reshaped our understanding of galactic dynamics is the presence of rogue stars. These celestial bodies drift through space without being bound to any specific galaxy, challenging the long-held belief that stars form in clusters and remain within their parent galaxies. Initially, scientists were puzzled by the existence of rogue stars, but over time, their discovery has revealed a complex web of interactions and processes that can eject a star from its galaxy. Gravitational interactions between stars, such as close encounters or collisions with black holes, can impart enough energy to a star to propel it into intergalactic space. This breakthrough has transformed our perspective on stellar formation, illustrating that stars are not confined to the boundaries of galaxies. The study of rogue stars provides essential insights into the broader structure and evolution of galaxies. These solitary wanderers offer clues about the mass distribution within galaxies and the pervasive influence of dark matter. Their unexpected trajectories serve as cosmic messengers, shedding light on gravitational forces that cannot be detected by traditional observational methods. By studying these rogue stars, astronomers can also gain a better understanding of how galaxies form and evolve, and how they interact over vast cosmic timescales. As researchers track the paths of these stars, they unlock new information about the processes that drive the formation and merging of galaxies. The ongoing exploration of rogue stars enriches our understanding of the dynamic, ever-changing nature of the universe, revealing that our cosmic reality is filled with surprises, often emerging from the most unexpected sources. Another key element in unraveling the mysteries of our galaxy lies in the study of binary systems, where two stars are gravitationally bound to each other and orbit around a common center of mass. These stellar pairs play an indispensable role in our comprehension of cosmic anomalies. By observing the behavior of stars in binary systems, astronomers can uncover vital information about stellar evolution, the nature of gravity, and even the fundamental physics of black holes. One of the most remarkable aspects of binary systems is their ability to offer precise measurements of star masses. When two stars orbit each other, scientists can apply Kepler's laws of motion to calculate their individual masses with extraordinary accuracy. These mass calculations provide crucial data for establishing models of stellar formation and evolution in a galaxy that is constantly in flux. The interaction between stars in binary systems also helps fill in critical gaps in our understanding of stellar life cycles and the formation of cosmic structures. As stars interact with one another, they can exchange mass, energy, and momentum, which alters their evolutionary paths. Binary systems serve as natural laboratories for studying more exotic and extreme objects, such as neutron stars and black holes. When one star in a binary pair reaches the end of its life, it may explode as a supernova, leaving behind either a neutron star or a black hole. If the remaining companion star is close enough, it may begin to accrete material from the remnants of its partner, leading to fascinating and complex phenomena. These interactions can produce high-energy events, such as X-ray bursts, which provide invaluable data for astronomers attempting to understand the most energetic processes occurring in the universe. Through the study of these binary systems and their extreme behaviors, scientists continue to push the boundaries of our knowledge, revealing the intricate dance of stars, galaxies, and the forces that govern the cosmos. These findings are not only expanding our understanding of stellar life, but also enhancing our broader comprehension of how the universe itself operates, constantly shifting, evolving, and surprising us with its complexity. Every discovery adds another layer to our understanding, inviting us to explore further and dig deeper into the mysteries of the night sky. In the realm of cosmic exploration, the study of binary systems, specifically how they respond to cosmic anomalies like gravitational waves, has significantly transformed our understanding of the universe. Gravitational waves, which are ripples in the fabric of space-time caused by massive celestial bodies accelerating, offer an entirely new way of observing the cosmos. When two black holes or neutron stars collide, the resulting gravitational waves travel across vast distances, carrying with them critical information about the origin of these events. This process not only enhances our understanding of individual stars within binary systems, but also serves as a crucial element in deciphering the broader narrative of our galaxy and beyond. The role of binary systems extends far beyond mere star observation. They act as keystones in the larger framework of cosmic research, connecting us to the fundamental forces shaping the universe. By detecting and analyzing the minute distortions in space-time created by these cosmic collisions, scientists are able to test and confirm theories of gravity, opening up new windows into the mysteries of space. These discoveries help map the very fabric of our universe, refining our understanding of celestial phenomena. However, the way we interpret such phenomena is not solely rooted in scientific inquiry. Cultural interpretations of the cosmos have deeply shaped the way societies view the universe, and in turn influence the methods scientists use to investigate anomalies. Throughout history, different cultures have attached unique spiritual or mythological meanings to the night sky. Celestial events, such as the movement of planets or the appearance of comets, were often perceived as divine omens or as signs of cosmic order, guiding everything from agricultural practices to religious beliefs. These interpretations formed the foundation for early scientific exploration, setting the stage for the first attempts to understand the cosmos. As modern science began to emerge, particularly during the Enlightenment, a clear distinction developed between scientific knowledge and cultural myths. However, The remnants of these early cultural interpretations persist, subtly influencing contemporary scientific thought. When scientists encounter unexplained phenomena, the cultural context in which these events are framed can guide the hypotheses they propose. For instance, the appearance of a comet in the sky might have been seen as a bad omen in ancient civilizations, but modern scientists approach the same event through a scientific lens, seeking explanations based on the object's trajectory and composition. Moreover, cultural beliefs continue to shape scientific priorities and funding, steering attention to anomalies that resonate most with public interest. When an event, like a supernova or a particularly puzzling astrophysical phenomenon, captures the imagination of society, it's not just the scientific mysteries that researchers must address, it's also the cultural narratives surrounding these occurrences. Public fascination with such events often leads to deeper engagement as scientists confront not only the hard questions about the phenomena, but also the social and cultural meanings ascribed to them. This intersection of science and culture deepens our understanding of both the cosmos and the human experience. By acknowledging the cultural narratives that shape our view of the universe, scientists are reminded that their work doesn't unfold in a vacuum. Instead, it is deeply embedded in a tapestry of human history, belief systems, and shared understanding. This holistic approach allows us to see cosmic anomalies not just as puzzles to be solved, but as integral parts of the human story, guiding us on our journey to comprehend the vastness of the universe. The discovery of other galaxies and the tantalizing possibility of multiple universes raise profound philosophical questions that challenge the very essence of our existence. If our galaxy is just one among countless others, what does that mean for the significance of humanity? Are we alone in the cosmos, or is there intelligent life elsewhere? These questions force us to confront our own identity and purpose, encouraging us to reflect on whether our lives hold meaning in the grand expanse of space. The concept of parallel universes only intensifies this contemplation, suggesting a reality in which different laws of physics or even alternate histories might unfold. This forces us to rethink the nature of fate, free will, and the choices we make. If every possible outcome exists in some parallel universe, it challenges our understanding of causality, destiny, and choice. The very act of choosing, of making decisions, takes on new significance when we consider the infinite possibilities available across alternate realities. In this way, the study of multiple universes may not only change our understanding of physics, but also reshape our view of the human condition itself. Furthermore, the existence of countless galaxies and potential universes invites a spiritual or existential inquiry. In a cosmos teeming with such diversity, what role does humanity play? This line of questioning can lead to a reevaluation of religious beliefs and concepts of creation, urging a closer look at the intersection between science and spirituality. As we expand our understanding of the universe, the boundaries between the scientific and the spiritual may blur, creating new philosophical paradigms that allow us to situate ourselves within the vast expanse of the cosmos. In this light, the discovery of other galaxies and the speculative notion of parallel universes invite us to explore the deepest philosophical questions about reality, existence, and meaning. Each new finding, whether it's the identification of distant galaxies or the possibility of other dimensions, opens up a pathway for reflection on the human experience. What is our place in this enormous and mysterious universe? What does it mean to be alive in a cosmos so full of uncertainty, wonder, and potential? Time itself, as a concept in cosmology, plays a crucial role in how we understand the universe. In classical physics, time is often viewed as a constant, a linear progression from the past through the present and into the future. This straightforward model allows us to treat time as a universal clock, ticking uniformly for all observers, regardless of their location or motion. Yet when we explore the universe through the lens of relativity, this simplistic view begins to unravel. Albert Einstein's theory of relativity introduced the revolutionary idea that time is not a constant, but a dynamic dimension intricately linked to space in a continuum known as space-time. According to this theory, time can stretch or contract depending on the speed of an object and the strength of the gravitational field it experiences. For example, an astronaut traveling near the speed of light would age more slowly than someone on Earth due to the effects of time dilation. This suggests that time is not an absolute entity, but a relative one, shaped by motion and gravity. Quantum mechanics, however, adds yet another layer of complexity to our understanding of time. At the quantum level, time may not follow the linear flow we associate with it in our everyday experience. Events can become entangled in ways that defy conventional notions of causality, leading us to question whether time itself could be perceived differently in the fundamental layers of reality. Could time, at its core, be a far more intricate and mysterious concept than we can imagine? This question lies at the heart of current scientific inquiry, pushing us to reconsider everything we know about the nature of time, space, and the universe itself. Cosmological models, particularly those involving the Big Bang and the cyclical universe, challenge the conventional understanding of time itself. In the Big Bang model, time as we perceive it did not exist before the explosion of energy that gave birth to our universe. This suggests that time, in its familiar form, may have begun only with the creation of the universe. Prior to that monumental event, the concept of time might not have had any meaning at all. There are also alternative models, such as those proposing an infinite cycle of expansion and contraction, which suggest that time could be experienced in an entirely different manner, subject to endless phases of cosmic rebirth. These models urge us to rethink our relationship with time, not as a passive backdrop to events, but as a dynamic and essential aspect of the cosmos itself. Through these various cosmological perspectives, time emerges not merely as a tool for measuring change, but as a fundamental force that shapes the very fabric of existence. The search for extraterrestrial life raises similarly profound questions, ones that are as much ethical as they are scientific. The idea of reaching out to potential alien civilizations brings with it both fascination and a host of complex moral dilemmas. Chief among these is the question of how to responsibly interact with beings from another world, should we ever make contact. A key consideration in this context is the potential consequences of sending signals into space. The famous Arecibo message, for instance, represents an attempt to communicate with distant civilizations, but it also raises questions about the ethical implications of announcing our presence to the universe. What responsibilities do we bear in broadcasting our existence to an unknown cosmos? There is a fear that such an announcement could attract unwanted attention, much like a signal in the night might draw the gaze of predatory forces. If an advanced extraterrestrial civilization were to intercept our message, could we be exposing ourselves to dangers we have not yet imagined? Another pressing ethical issue involves the potential exploitation of any discovered civilizations. If we were to encounter a technologically superior species, questions of power dynamics would quickly arise. Would we approach them as equals, or would the temptation to manipulate or exploit their resources prove irresistible? Many scientists and ethicists wonder whether humanity is truly prepared for such an encounter. Are we equipped to engage with a civilization that is radically different from our own, and do we possess the moral framework to treat such beings with respect? In addition, there is the issue of human bias. We are inherently inclined to judge other forms of life by our own moral and cultural standards, a tendency that could lead to misinterpretations of their actions or intentions. It is increasingly clear that intelligence and culture may manifest in forms we have not yet conceived, and our ethical responsibility is to remain open-minded, careful not to impose our values on others. Finally, the discovery of extraterrestrial life presents a fundamental existential challenge. How would such a discovery reshape our understanding of ourselves and our place in the cosmos? The implications could be nothing short of transformative, influencing everything from philosophy to religion, from scientific inquiry to societal norms. In this vast and mysterious universe, the excitement of discovery is weighed against the profound ethical questions that accompany it. Every new possibility forces us to reconsider what it means to be human in a cosmos teeming with potential. Scientists must navigate this delicate balance, constantly asking, how should we proceed in the vastness of space, where the unknown holds infinite potential and peril? Our understanding of the universe profoundly shapes human consciousness and culture. influencing everything from belief systems to artistic expression. Throughout history, the cosmos has inspired countless forms of creative and intellectual exploration, from the ancient Greeks' awe of the stars to the Renaissance's celestial-themed artworks. The universe has captivated the human imagination, raising essential questions about existence, purpose, and the nature of reality itself. As we have developed more sophisticated scientific tools such as telescopes and space missions, our view of the universe has shifted dramatically. No longer is the cosmos a static backdrop to human life, but a dynamic, ever-evolving entity in which we are a small part. Consider how the discovery of the Big Bang Theory changed our understanding of the universe. It revealed that the universe had a beginning, a singular event that set everything in motion. This realization has profound implications, suggesting a deep interconnectedness among all forms of matter and energy. This concept has seeped into broader philosophical discussions, shaping modern existential and ecological thought. It also challenges us to rethink our place in the universe, especially as we come to terms with the fact that Earth is merely a tiny speck in an overwhelmingly vast cosmos. This knowledge encourages humility, urging us to reconsider our relationship with the environment and our responsibility to protect it. The growing awareness of climate change, fueled by scientific discoveries, has fostered a global consciousness about the need for sustainability. This ecological awakening is shaping a new societal narrative, one that prioritizes compassion for all living beings and underscores the interconnectedness of life on Earth. It is not just the universe beyond our planet that calls us to reflect, but the very Earth itself. Our exploration of space, in a sense, forces us to transcend our individual concerns and think collectively, as we are all inhabitants of the same fragile world. The quest to understand the cosmos thus becomes a shared endeavor, one that unites people across cultures and backgrounds, reminding us that despite our differences, we all share the same sky. This intersection of science, art, and philosophy creates a rich tapestry of human culture. It is a reflection of our ongoing quest to understand the universe, and in doing so, to better understand ourselves. Philosophical perspectives have long played a crucial role in shaping how we interpret cosmic mysteries. Thinkers have pondered the nature of existence, the origins of the universe, and the role of humanity within it. This philosophical inquiry often intersects with cosmology, offering frameworks that help us grapple with the vast, often unfathomable phenomena of the cosmos. For instance, the timeless question of why there is something rather than nothing invites not only scientific exploration, but deep existential reflection. Cosmologists strive to understand the origins of the universe, leading to groundbreaking concepts such as the Big Bang. Yet, philosophical perspectives urge us to consider the broader implications of these discoveries, especially when it comes to the meaning they hold for humanity. This interplay between science and philosophy opens a dialogue about the limits of human understanding and the mysteries that may always elude us. As we explore the cosmos, we confront not just the vastness of space, but the limits of our own knowledge, reminding us that there is still much we do not, and may never, understand. Cosmic phenomena have long fascinated humanity, and different philosophical traditions provide unique lenses through which we can explore these wonders. In Eastern philosophies, particularly Buddhism, there is a profound emphasis on the interconnectedness of all things. This worldview resonates strongly with some of the most intriguing ideas emerging from modern scientific inquiry, especially quantum physics, where the boundaries between the observer and the observed blur, suggesting that everything in the universe is interdependent. The fabric of spacetime itself, as theorized in Einstein's theory of relativity, further supports this idea, presenting the universe not as a series of isolated events, but as a dynamic, interconnected whole. This framework calls into question the separateness we often feel from the cosmos and invites a new way of thinking about the world around us. On the other hand, Western philosophy often wrestles with the dualities of mind and body. This intellectual struggle, dating back to the early works of Plato and Descartes, still shapes how we think about consciousness and its relationship to the universe. Are we merely physical beings, or is there something transcendent within us that connects us to the greater expanse of space? This tension between the physical and the metaphysical plays a central role in how we interpret human existence and our place in the cosmos. This philosophical diversity enriches our understanding of the universe, providing a nuanced and multidimensional view of cosmic mysteries. While scientists gather empirical evidence to uncover the laws governing the universe, philosophers urge us to consider the deeper whys behind those discoveries. The union of science and philosophy not only satisfies our intellectual curiosity, but also nurtures a deeper wonder about the cosmos. Through this collaboration, we are invited to engage with questions that have no clear answers, fostering an appreciation for the unknown. This approach encourages us to dream, reflect, and seek meaning, particularly when we look up at the stars. A central concept that has captivated thinkers throughout history is the idea of infinity. This abstract notion is essential to our understanding of space and many of the anomalies that occur within the cosmos. As we peer into the vast expanse of the universe, we are confronted with the possibility that space itself might be infinite. This challenges our perception of boundaries and limitations and raises profound questions about what exists beyond the edges of our observable universe. What lies beyond the cosmos we can observe? Is there an end, or does infinity stretch onward in all directions? Astronomers have discovered enigmatic phenomena like black holes and dark matter that force us to reconsider what we know about infinity. Black holes, with their immense gravitational pull, warp the very fabric of space-time, creating regions where conventional rules break down. At the event horizon, the boundary beyond which nothing can escape, not even light, time behaves strangely. To imagine a traveler approaching this boundary is to imagine someone who experiences time differently from an observer far away from the black hole. This paradox underscores how infinity can distort not only space, but also our understanding of time itself. Additionally, the very structure of the universe challenges our comprehension of infinity. Theories such as the multiverse suggest that there might be countless other universes existing alongside our own, each governed by its own set of laws of physics. If true, this idea would extend the concept of infinity beyond the observable universe, suggesting an endless number of realms that are currently beyond our understanding. This exploration into the nature of infinity pushes the boundaries of what we know, and yet, as we dive deeper, we realize that the more we discover, the more there is left to explore. The expanding universe further ties into the concept of infinity. As we observe the distant galaxies moving away from us, it becomes evident that the universe is not only vast, but also growing, stretching further and further outward. This raises profound questions. Will the universe continue to expand forever, or will it eventually reach a point of equilibrium, where expansion ceases? The very idea that space might go on indefinitely challenges our sense of self-importance, suggesting that we are merely a tiny speck in an enormous, infinite cosmos. This ongoing exploration into the nature of infinity fuels our curiosity and drives us to seek the ultimate secrets of existence. The portrayal of space in art and literature has also played a crucial role in shaping the public's understanding of scientific discoveries. From ancient mythologies to modern science fiction, art has provided a platform to imagine and explore the cosmos in ways that are emotionally resonant and intellectually stimulating. Artistic expressions allow us to grasp complex scientific ideas by transforming them into stories we can relate to, enabling us to envision the unknown through a human lens. One striking example of this is Jules Verne's From the Earth to the Moon, written in the 19th century, long before actual rockets were even conceived. The novel not only entertained readers, but also inspired them, capturing the imagination of the public and fostering a collective belief in the possibility of space travel. Similarly, the works of artists like Vincent van Gogh, particularly his painting Starry Night, have become iconic representations of the night sky, inspiring wonder and curiosity about our place within it. Such works do not just evoke beauty, they provoke thought, encouraging us to look deeper into the mysteries of the universe. In the 20th century, films like Stanley Kubrick's 2001: A Space Odyssey brought space exploration to life on the big screen, introducing audiences to scientific ideas in a format that was both accessible and visually captivating. These cinematic portrayals often blend science fiction with real scientific discoveries, helping to popularize complex concepts while igniting public discourse around space exploration. Moreover, these representations can sometimes spur technological innovation. When fictional technologies are envisioned in films, scientists and engineers are often motivated to bring them to life, bridging the gap between imagination and reality. Art and literature also serve a deeper function, addressing the philosophical and existential questions that arise from our exploration of space. These works explore the emotional and psychological challenges that come with confronting the unknown, with the awe and fear that accompany our pursuit of understanding. By framing scientific discoveries within human stories, art allows us to reflect on our desires, fears, and aspirations about the cosmos. This intersection of creativity and science enriches our understanding, transforming the mysteries of space from mere facts into a part of a broader human narrative. Finally, the anomalies we encounter in space, those perplexing phenomena that defy our understanding, often provoke profound philosophical reflections about fate, free will, and the nature of existence itself. When we look at the universe, we observe a vast array of forces and laws that govern everything from the formation of stars to the rotation of galaxies. These predictable patterns can lead us to wonder. Are we simply following a predetermined path, or do we have the agency to shape our own futures? Is the cosmos governed by laws that leave no room for freedom, or is there room for randomness and choice amidst the vastness of space? As we continue to explore the universe, both through scientific inquiry and philosophical reflection, we are reminded that the questions we ask are just as important as the answers we seek. The pursuit of knowledge is not just a quest to understand the mechanics of the cosmos, but a journey into the very nature of existence itself. Through this process, we learn that the universe is not just a place to study, but a profound mystery to experience and contemplate. However, the very existence of anomalies like black holes and the mysterious behavior of dark matter introduces an unpredictable layer to our understanding of the cosmos. The notion that the universe operates with a degree of determinism is increasingly complicated by these phenomena, which defy easy explanation and often seem to govern the fate of the celestial bodies around them. Take, for instance, the extraordinary way in which black holes warp the fabric of space-time. Not only do they exert immense gravitational pulls that can alter the paths of nearby stars, but they also generate such intense heat that surrounding matter is torn apart and heated to extreme temperatures. In these conditions, the destiny of nearby objects, whether they are planets, stars, or even light itself, can be irreversibly shaped. This raises profound questions. Do these cosmic forces suggest that entities, be they stars, planets, or even human beings, have any true control over their paths? Are we, in a sense, at the mercy of forces that are beyond our comprehension? Black holes, with their immense gravitational power, seem to dictate the very fate of everything within their reach, leaving us to wonder whether any form of control or free will can exist in such an environment. When the universe contains centers of such intense manipulation, does it diminish our sense of agency, or does it merely invite us to reconsider how we navigate our choices within a larger, more mysterious design? On the other hand, these very anomalies also represent the unexpected, the unknown, what some might even call the hidden opportunities of the cosmos. Each time scientists encounter a phenomenon they cannot immediately explain, it opens the door to new realms of understanding and innovation. In this sense, black holes and other anomalies are not just challenges, they are gateways to discovery. The very existence of such mysteries encourages us to look at free will in a new light. Free will, perhaps, isn't merely about making decisions. It is also about responding to the unpredictable nature of existence itself. In the chaos of the universe, amid the quirks and peculiarities that define its vastness, there is room for action, creativity, and even beauty. Just as the universe seems to throw up surprises and anomalies that change the course of its evolution, our lives too are punctuated by events that alter our trajectories in ways we cannot predict. Each decision we make feels deeply personal, yet we are also constantly influenced by a web of circumstances that stretches far beyond our immediate understanding. Perhaps By recognizing the anomalies in space, we can find a parallel in our quest to understand fate and free will. While destiny may indeed set the stage, it is our choices that shape the narrative of our lives. Cultural beliefs about the cosmos have been intricately woven into the fabric of human history. From the earliest civilizations to the present day, how people perceive the universe has influenced their lives, values, and even their scientific pursuits. For example, many ancient cultures viewed the stars not just as distant objects in the sky, but as gods, ancestors, or spirits guiding the course of human events. This deep sense of connection between life and the cosmos forged a worldview in which human actions were inseparable from the larger workings of the universe. Even today, many cultures hold on to these traditional beliefs, influencing how they interpret astronomical phenomena. While the advent of modern science has greatly expanded our understanding of the cosmos, these diverse cultural perspectives continue to play a pivotal role in shaping the way we think about the universe. Today's cosmology is not just a product of mathematical equations and astronomical observations, but is also enriched by philosophical questions rooted in ancient narratives and belief systems. The way we perceive abstract concepts such as time, space, and existence can vary greatly, depending on our cultural backgrounds. This rich tapestry of perspectives encourages scientists to engage in interdisciplinary dialogue, fostering a deeper and more holistic understanding of the universe. Moreover, the intersection between science and culture holds the potential to make astronomy and other fields of science more inclusive. By acknowledging the value of different cosmological beliefs and engaging with them respectfully, scientists can broaden their reach, connecting with audiences who might not otherwise have been drawn to the sciences. This, in turn, could inspire a new generation of scientists from diverse backgrounds to pursue careers in fields like astronomy, bringing their own unique cultural perspectives to the exploration of the cosmos. The dialogue between scientific inquiry and cultural beliefs is not merely a coexistence, but an active shaping of how we understand the universe. Cultural narratives enrich scientific inquiry, suggesting that science is not just the search for knowledge, but a collective journey through the cosmos, a journey that reflects the diversity and complexity of the human experience. This collaborative approach fosters a deeper sense of curiosity and shared purpose, reminding us that the pursuit of knowledge transcends borders and is rooted in the universal desire to understand the mysteries of existence. Astrophysics, the study of the universe and its phenomena, remains one of the most fascinating and complex fields of scientific inquiry. Despite the remarkable advancements in technology and observation, many questions about the universe remain unanswered. One of the most pressing mysteries in modern astrophysics revolve around dark matter and energy, which together make up approximately 95% of the cosmos. These components remain elusive, as they neither emit, absorb, nor reflect light, and their properties are yet to be fully understood. Their mysterious nature forces scientists to reconsider the very foundation of what the universe is made of, raising questions about the fundamental structure of the cosmos itself. Equally tantalizing is the question of extraterrestrial life. Despite decades of searching, scientists have yet to find definitive evidence of life beyond Earth. This ongoing quest has sparked a myriad of hypotheses about what conditions might be required for life to thrive elsewhere in the universe, and whether intelligent civilizations might exist on distant planets. The exploration of other worlds, such as Mars and the moons of Jupiter and Saturn, remains a focal point in the search for extraterrestrial life. With each new discovery, our understanding of the conditions that could support life expands, and the possibility of life beyond Earth becomes more real. Another profound mystery that continues to captivate the scientific imagination is the enigma of black holes. While much progress has been made in understanding the formation and basic properties of these cosmic giants, many questions still remain. For example, what happens to the information that falls into a black hole? This so-called information paradox challenges our understanding of the laws of physics, particularly the nature of space, time, and reality itself. The study of black holes has led to the discovery of gravitational waves, phenomena that have opened up new avenues for exploring the mysteries of the cosmos. Finally, the ultimate fate of the universe remains an open question. Will the universe continue to expand indefinitely, or will it eventually collapse back in on itself? The nature of cosmic expansion and its long-term implications for galaxies, stars, and planets is a topic of intense debate. As astronomers gather more data from distant galaxies and refine their models, they inch closer to understanding how the universe will evolve over the coming eons. However, each discovery only raises new questions, ensuring that the field of astrophysics remains vibrant, full of wonder, and open to infinite possibilities. In essence, the universe is vast, mysterious, and ever-changing. Our understanding of it is still in its infancy, and with each new discovery, we are forced to rethink our place within it. From the detection of gravitational waves to the exploration of dark matter and dark energy, these breakthroughs challenge existing paradigms and deepen our understanding of the cosmos. As technology continues to advance, we will undoubtedly encounter phenomena that we cannot yet imagine, and with each revelation, our view of the universe will expand, perhaps beyond what we ever thought possible. The search for exoplanets in the habitable zones of distant stars is an exciting frontier in our understanding of the cosmos. These discoveries suggest that the possibility of life beyond Earth is no longer confined to the realm of science fiction. Whether we eventually encounter microbial life or, more profoundly, intelligent beings, the implications for humanity would be revolutionary. Such a discovery would challenge our conception of life's rarity and our place in the vast universe. It could spark deep philosophical debates on the interconnectedness of all living beings, raising profound questions about the very nature of existence. In parallel, as we delve deeper into the cosmic background radiation and investigate the origins of the universe itself, we may uncover evidence that compels us to reimagine our entire cosmological framework. Each new finding could challenge or reaffirm our current theories, sometimes supporting our established views, while other times demanding a complete reassessment of everything we thought we knew about the fabric of reality. The future of cosmology, with all its mysteries, holds endless potential for new discoveries that could completely reshape our understanding of the universe. As we journey through life, our personal experiences play a significant role in shaping the way we perceive the cosmos. For example, a peaceful walk along a familiar path, with the rustling of leaves above and the comforting silence around us, can subtly remind us of nature's cycles and the larger patterns that govern the universe. These moments of solitude inspire contemplation, nudging us to reflect on our place in the grand expanse of space. Stargazing, for instance, provides an awe-inspiring way to connect with the cosmos. Imagine lying under a blanket of stars, the Milky Way stretched across the sky like a glowing river. Each point of light represents a distant sun, and with every glance upward, we are reminded of the vastness and complexity of the universe, an endless sea of stars, each one part of something much larger than ourselves. Personal encounters with science, whether through an engaging book, an insightful documentary, or a thought-provoking lecture, can open our eyes to the universe's underlying principles. These moments of discovery allow us to connect the dots between the smallest particles and the largest galaxies, deepening our appreciation for the incredible forces that shape the world around us. With each new insight, we are not merely adding to our knowledge, we are also transforming curiosity into a thirst for further understanding. It is this continuous journey of exploration, fueled by moments of wonder and sometimes even confusion, that keeps us asking questions. Whether it's the mysteries of space, the complexities of life, or the fundamental laws that govern the universe, these inquiries keep us moving forward. Each discovery, no matter how small, brings us one step closer to understanding the breathtaking mysteries hidden within the vast reaches of space. Public engagement with space exploration is an intricate balance of education, inspiration, and relevance. As the pace of scientific discovery accelerates, it becomes even more crucial to highlight the tangible benefits that space research brings to our everyday lives. For instance, innovations born from space technology have revolutionized fields like telecommunications, healthcare, and weather forecasting. By showing the practical applications of space research, we can help the public understand how space exploration directly impacts them. Engaging storytelling plays a key role in maintaining public interest and support. By humanizing the stories of scientists and astronauts, we can foster a personal connection to space missions. Sharing narratives about the challenges faced in space, the triumphs of human ingenuity, and the dedication of those working to explore the unknown, we capture not just minds, but hearts as well. Moreover, the inclusion of diverse voices and experiences in these stories makes them more relatable and broadens their appeal. Hands-on experiences, too, offer a unique way to stoke interest in space exploration. Interactive exhibits, virtual reality experiences, and community events allow the public to engage directly with the subject, creating a more immersive and meaningful connection. Additionally, educational initiatives, especially those targeted at young minds, have the power to ignite a passion for space and science. Schools and universities can be crucial in fostering the next generation of explorers, scientists, and dreamers. Effective communication is another cornerstone of keeping public interest alive. Regular updates from space agencies, scientists, and educators about missions, discoveries, and upcoming events can keep the excitement alive. Social media platforms, with their ability to share visually compelling content and groundbreaking findings, provide an ideal medium for reaching a wide audience. Community outreach programs, too, help spark conversations about the importance of space exploration and its role in shaping our future. Ultimately, the goal is not just to sustain public interest, but to inspire, educate, and create a deeper, more personal connection to the wonders of the cosmos. Weaving together inspiration, education, and hands-on engagement creates a vibrant atmosphere where curiosity can thrive. The pursuit of space exploration, particularly the study of cosmic anomalies, transcends individual achievements. It taps into our collective curiosity about the universe and our place within it. The legacy I hope to leave is one that sparks imagination and wonder in future generations. When young minds encounter the mysteries of black holes, dark matter, and other cosmic phenomena, it fuels their sense of inquiry, potentially leading to groundbreaking discoveries that will reshape our understanding of the universe. I envision a legacy rooted in collaboration, one that encourages the blending of multiple disciplines. The study of space is not confined to astronomy alone. It spans physics, chemistry, and even philosophy. This interdisciplinary approach enriches our understanding of the universe, and by advocating for such cooperation, I hope to inspire future scientists, artists, and thinkers to work together in breaking down silos and producing more holistic insights. In addition, I hope that this legacy will foster a sense of stewardship for our planet. As we gaze into the infinite cosmos, we are reminded of the fragility of Earth. The exploration of space anomalies can provide valuable insights into our planet's history and future, prompting us to take more responsible action in both science and conservation. The pursuit of knowledge, after all, should not only enhance our understanding of the universe, but also promote a sustainable future for all life on Earth. In conclusion, the aim is not just to contribute to scientific knowledge, but to inspire wonder, promote collaborative exploration, and cultivate a sense of responsibility toward our planet. The study of space anomalies holds the potential to pave the way for a brighter, more interconnected future, one where curiosity leads us to new discoveries and a deeper understanding of the universe and ourselves.